First of all, I have the honour to introduce Auntie Marie Taylor. Auntie Marie is a Whadjuk Noongar elder and the chairperson of the Yellowkitch Nort Noongar Association, and she is going to do our welcome to country today.
Thank you. I'd like to welcome you all here to the most ancient of Aboriginal land in the world, Noongar country. And I'm going to welcome you in the ancient language of Noongar to my country. Abba, Whadjuk Baladong Noongar Budi Yok Wanju Wanju Noongars, Noongar Wom, Wedgelas, Budias, Nitiyokania Bibbleman Borja, Nitawardang Mat Management Kundam Borja, Murt Jenabidi Nitabalapin Weir Mit Yinin Yalakan Yai Ne, Karajenang Kora Yai Buddha. Greetings, the Aboriginal custodian welcomes you all here to the land of the people of many breast. This is Crow and Cockatoo dreaming land, whose families and ancestors tread the grounds, leaving footprints upon the land where their spirit lingers on, surrounding us through stories as we listen, look, learn, talk, and later on we will celebrate. Nunakan Kurin Kumbawaran Pakija Alijanuna Borja Ual Kurnicha, Belia Borja, Wanju. Some of you may have come from over the Great Sea or from your lands afar to come and settle on the land of the waters at Belia. I warmly welcome you all here today. Shuai Wara Wirn Buyaka Buyaka, Muriap Murichwir Nichakarang Nodachi Bornawanki. I've asked the bad spirits to leave the room, the good spirits to come and be with you all today. And as I leave the Karang Nodachi, it is the message stick of peace. I don't come in anger. We have 6 seasons. And the season that we are in today is Camberang. And it is the season of the black crow, Wardong, who's flying around everywhere. It is also the land of Wannel, the peppermint tree that grows everywhere out in our country. And also the famous land for that beautiful tree, Mudja, the Christmas tree. And I've seen one finally starting to flower as I was driving up, coming with my daughter from Kwinana. They're just 3 totems of our seasons. We have 6 seasons, and many of those seasons are cared for by the Noongar people still today. And I encourage you all to connect with the Aboriginal community that works here, not only in the city, but also down in the country. I'd like to leave a blessing with you all in case we never meet here again on Noongar country. Ngalakan Kenin Murt, Ngalakan Bulla Murt, Ngalakan Bulla Borjak Ual Kor, Yakani Ngalakundam, Doinch Warakan, Ngan, Nunuk, Ngalak, Murich Murt, Anna. Yes, we are one, but we are many, and from all the lands on earth we come. We share a dream and sing with one song. I am, you are, we are solid Australians. Yunka, thank you. And hopefully our team will win the grand final next year. Yunka, thank you everybody.
Thank you, Auntie Marie. I seen you give a welcome so many times, and every single time I see you, I learn something new. There's always a little extra tidbit of information that I haven't heard before, and I really thank you for that. Today, we've got a whole lot of different speakers here covering quite a few different parts of government and research, and I really hope that you're going to enjoy this whole session. So, first of all, I completely forgot to introduce myself. So I'm Trina Burgess. I'm the Executive Director of the Harry Butler Institute here at Murdoch University, and our research focus is around environmental sustainability, and today we're just really happy to be sponsoring this event and to be able to hold it here in the Rosemary Vanderberg room, which is really a very, very beautiful place. So our first person that we're going to have here today is Alistair Jones, who is the Director General of DWER, the Department of Water and Environmental Regulation. He joined the department in January 2024, and he came with 15 years of leadership and experience in government. He's passionate about protecting WA's environment and water resources and champions innovation, data analytics and strong partnerships with Aboriginal communities to guide the department's work. So welcome, Alistair.
Thank you. It's so great to be in this building. This is the second time I've been here. I was at an event last year for greening and increasing canopy cover, and we had it outside. But I'm still never ceased to be amazed by the architecture of this building. I mean, it's amazing. Look, good afternoon, everyone. I'm not going to speak for long because I had a look at the agenda and some really interesting stuff here. And as what Tran has said before, is I came from another government agency. I actually came from Treasury, and probably when I first arrived at DWER, I described myself as the chief data nerd of government. So yeah, data analytics is something that I did in my previous job. But when reading the agenda and the work that's going to be showcased here today, I got really excited. So my data nerdness has come to the fore, and I'm really looking forward to listening to some of the presentations. Look, Minister Don Punch was going to be here, and they've got this pesky thing called pairs in the Parliament, and for some reason he couldn't get a pair. For those of you who don't understand the Parliament, a pair is when someone from the opposition side isn't there as well, and sometimes when they're falling out, they don't give each other pairs. I don't know if that's the case today, but he gives his apologies and is really disappointed that he's not here. I mean, Emily Briggs, who's one of my deputies, we were just at a meeting with the Minister before, and he was really looking forward to coming down here. So I've kind of got to step up to the breach a little bit. Auntie Marie, thank you very much for welcoming us to country, and I'd also like to acknowledge that we're meeting on Wajak Noongar Budja, and I'd like to pay my respects to you, to other elders, both past and present, and also pay my respects to Aboriginal people that are either online or in the forum today. I mean, one of the things about being a regulator is often we take a Western science view of the world, but what we're trying to strive for at the department is to actually tap into that deep knowledge. I mean, you've been caring for country and water for probably close to 100,000 years. We've only been doing it for probably about 100, and I think you did a better job than what we're doing, but we can use some of Western science and meld it with that traditional knowledge of country, and hopefully care for country going forward, because that's really my primary desire as Director General of the department. All right, the other thing that I want to also acknowledge too is Mr. Mark Stickles. Where are you, Mark? I don't think I met you before, from Pawsey Supercomputing Research Centre, which is around the corner from my house. And I learnt from reading my speech notes, it's a green supercomputer, so I might grab you after and figure out how that is. And also Professor Peter Eastwood, Deputy Vice-Chancellor of Murdoch University, and look, just basically acknowledge your critical contributions to this climate science initiative. And I think we were joking earlier, I didn't know who you were when you said you were Peter. It hadn't joined the dots that you're actually Trina's boss and head of the school. So as Director General of the department, it's my pleasure to be here today to open the forum and also talk about some important work that the department is doing to basically help our community understand and adapt to the impacts of climate change and also support the government's commitments for climate resilience. So you probably noticed after the election we used to have one minister, we've now got two. And part of that, I think, was basically a recognition that we need to be more resilient in dealing with climate change, and this type of science is integral to doing that. So rather than splitting the one role, I think what the government did and the Premier did in consultation with the ministers was to split the two functions, and especially with Minister Punch, water is a key component in climate resilience, and it's a really important element of our climate resilience journey. So having a Minister for Water who's also a Minister for Climate Resilience, I think is a really important thing to get initiatives going. Now, we live in West Australia's southwest, and I was talking to one of my staff who's come back from America. We did have a joke that he came back because of the change of government over there and the current administration, that climate science is probably not the most popular thing in the US at the moment under the current President, but welcome back, and it's great to have that international expertise coming back to WA and working with others. So really, we live in what is acknowledged as a global climate change hotspot. And since I've been Director General, driving around, remember last year, I grew up in the southwest, I'm a Bunbury boy, looking at the change, the stress on the trees, looking at the water impact of climate change, and also the impact of what we do as people on the environment was really confronting for me. So climate change is real. I know some people don't think it is, but I think it is real, and the science backs that up. So it's really great that initiatives like this are going to help us deal with this ongoing challenge going forward. Look, the other role that we've got is responsible for managing and regulating our water resources and also our environment, and that's a tough job. It's balancing competing priorities. People need places to live. We have to mine because we obviously need money for our economy to grow. But also, we need to be aware that we've got to protect natural ecosystems, we've got to protect species, and we've got to make sure that we actually leave our little bit of the earth as a sustainable place for our kids and our grandkids. And as a parent, that's really important to me. Managing water is really critical to our aspirations and livability and a thriving economy, and we are really working hard in terms of water management and climate adaptation, and we are having to do some accelerated work to catch up. I was up in the Pilbara probably about 10 days ago with the Minister and actually looking at the impact of climate change and other activities that we do on the environment, and seeing pictures of what it looked like 3, 4, 5 years ago compared to what it looks like now. It really does bring it home, and I was lucky enough to be on country with the Robe River Kurrama people who their country's near Pannawonica, and then we also spent a day with the Yindjibarndi Nation up at Millstream, having a look at what we can do to work together with them. And there was a $12 million announcement where we're doing some more science and also tapping into traditional knowledge to look after the water resources in the Pilbara. So I think that work will be rolled out through the state. We had a climate adaptation strategy in 2023, and that keeps Emily and Sarah Gill really busy, and that's got 37 priority options and about $100 million worth of funding. And that's really just a first step in is embedding our response to climate risk and adaptation across the sectors, and I think what you'll see over the next probably decade is that effort rolling out and becoming really business as usual as we run state government. But that key initial work is well underway, and it's working well. It's had little bumps every now and then, but people are embracing it, and it's really setting us up to be equipped to deal with climate change going forward. Now, you talk about climate change, but without climate science, we're not going to be able to measure where we've come from and where we're going to go. And it's really essential for understanding the impacts of climate change. And you as a collective group are so important to build that knowledge and that capability locally here in Western Australia. And I've had a look at a few of the sponsors around here, and it's great to see. I did see New South Wales up there, and it's great we're collaborating with on a national level, but like Murdoch University, Pawsey, I know you're based at Curtin, we've got the Harry Butler Centre, I mean, we've got the department as well, so it's great that we're all working collectively to build our capability and capacity in that, and also working with our federal colleagues. Now, again, today's forum is the Climate Science Initiative, and that's an investment of more than $7 million, and it's delivering on some key government commitments for climate resilience. The program's producing the most detailed and comprehensive West Australian climate change projections to date, extending to well beyond when I'll be on the Earth in 2100, and the program will also ensure that the decisions we make now and into the future are based on the best available science, and that's really important. Having been around politics, some of the worst decisions are made by emotion and not by science, and having evidence-based policy making and decision making is incredibly important, and you will play a key role in building that capability and advising us all the way through. Under the CSI, the department's partnered with some leading scientific institutions to simulate future climate conditions at 4 kilometres and 20 kilometre resolution. So I had this explained to me before, and I think it's really cool. The work that New South Wales has done is basically from 100 down to 20, and then we're doing from 20 down to 4. So the data nerd in me and especially the visualisation stuff got very excited, so I might have to pay you a little trip down to Pawsey and have a look at it at first hand as well. And this level of detail is really, and the regional specificity is the first for Western Australia, and part of that, you talked about Noongar country. We're a big state, and you go around the state and the environment's not the same everywhere we go. Country all over the state is a lot different, and it's got its own unique natural ecosystems and climate as well. So we partnered with Murdoch University in 2022 to deliver the projections and build local climate expertise, and we're now supporting and investing in the next generation of climate scientists in Western Australia, and I think we're supporting 2 PhD scholarships here at Murdoch, and you'll hear more about their projects later today. Now, I haven't met you. Are you one of the PhD people? Or if you're in here, put your hand up, or you're the boss. So you won an award the other night, didn't you? I shouldn't insult you by that. Yeah, you did talk about your team. So who are the PhD students? Put your hand up. All right. Good to see you. It'll be great to hear about your projects going further now. Again, we've joined the next generation of the New South Wales and Australian Regional Climate Modelling Project, and that's great that we're working together nationally. And also in 2023, the partnership with Pawsey started. Now, I've learnt something today, and that is Cetornix, which is Pawsey's computer, is named after the scientific genus name for the quokka. So when I go home and have a discussion with my daughters around the dinner table today, I've got my fact for the day, which is Cetornix, I don't know if I'm pronouncing this right, Brachyius is the most powerful research computer in the Southern Hemisphere, and it's named after the quokkas. And it's capable of calculations in 1 second that would take a human 1.5 billion years to do. So that's a pretty awesome stat, and I'll share that with my daughters this afternoon. So what's Cetornix going to do? It's going to deliver projections of how the state's climate will change over the next 75 years and basically look at including forecasted rainfall and temperatures under different emission scenarios. So the beauty of models is running scenarios and crunching the numbers. So it looks like you can do a fair bit of crunching with that supercomputer power that we've got. Now, we can do all of this science, we can do the work, but probably a key thing with science, and some of you who are academics will know this, is then getting that work and communicating it to the broader community and actually making it relevant to them. So the Climate Science Initiative in WA is also about connecting capability with WA's specific needs. So it's looking at building interactive tools, guidance, fact sheets, and hosting events like today to ensure that climate science is understandable and it's usable by everyone from households to technical experts, and that is really important. It's really important that everybody knows the impact of climate change and what we're going to do to fix it, and all do their fair share. So today you'll hear from the talented people in the department's Climate Science Initiative on the next steps for this program, as well as scientists here at Murdoch University. Look, we're proud to support this work, in ensuring that climate information is translated to actionable outcomes, and we're also empowering West Australians to prepare for these challenges that I discussed earlier. So thank you for your continued support, and I look forward to the conversations this afternoon and the collaborations that may emerge from today's event. Thank you.
Thank you very much, Alistair. That was very informative, actually. I know a lot more about how DWER operates now. Next, I'd like to ask Professor Peter Eastwood to come to the stage. Peter is our Deputy Vice-Chancellor of Research and Innovation here at Murdoch University. He's been here for more than 2 years now, so I think he's getting to know us pretty well, and he will give us a welcome from Murdoch. Thank you.
Thank you, Trina, and thank you very much, Auntie Marie, for your welcome to country. I'm not sure if we support the same football team, but if it's the West Coast Eagles, the chances of them winning a grand final next year will take an absolute miracle, I think. You've got a lot of chance if it is the Dockers, so I wish you luck. It is a great pleasure to welcome you all to Murdoch University and to Bulakatajan, which is the Noongar name for lots of learning. This is my favourite room in the entire university, and every time I come here, from this angle, I look out over the Banksia woodlands and the Beliar wetlands. And it doesn't take much to imagine the learnings which have gone on in this country for the past 65,000 years. And Murdoch University is genuinely proud to be continuing those learnings here on its southern campus. I too would like to acknowledge the Whadjuk and Binjarab Noongar people and pay my respect to their elders past and emerging. And I note again this land has been a place of learning for thousands of years, and we are proud to continue that tradition today. Today's Climate Science Initiative event brings together stakeholders from across Western Australia to share the latest scientific advances and practical tools that will help shape our state's climate resilience. The Climate Science Initiative, a $7.35 million partnership led by DWER, Murdoch University and Pawsey Supercomputing Centre and the New South Wales Government, is delivering the most detailed climate projections for Western Australia to date. However, today's event is relevant to all Australians because many parts of our country are living through a period of long-term drought and increasing climate variability. Our region faces significant challenges, and the need for accurate, localised climate information has never been greater. That's why the high-resolution 4-kilometre simulations developed by Dr. Jatin and his team are so significant. As mentioned by Alistair, these simulations represent a leap forward in our ability to model precipitation and, crucially, to predict high-impact weather events such as hailstorms that global models simply cannot capture. So let me take you back to March 2010, when Perth experienced the most expensive natural disaster in Western Australia's history. It was called the Great Hailstorm, which struck our city and caused over $1.3 billion in damage, with hailstones up to 6 centimetres in diameter, flooding and widespread destruction across homes, schools and even historic buildings. It was called a 1-in-100-year event, and it underscored just how vulnerable our communities and infrastructure are to extreme weather. Importantly, the new 4-kilometre regional climate simulations are able to reproduce such events, giving us a much clearer picture of the risks we face and how they may evolve in the future. By comparing these simulations with real-world observations, we can better understand what the future holds for our region, and importantly, we can plan and adapt accordingly. This work is not happening in isolation. It's the result of strong partnerships between government, academia and the Supercomputing Centre. The WA Climate Projections Viewer, for example, will make these complex scientific insights accessible to planners, policy makers and the wider community, empowering everyone to make informed decisions. At Murdoch University, this research aligns directly with our strategy and our values. Our vision is to be a leader in sustainability, education and impactful research, creating solutions for a better and more sustainable world. We are committed to partnerships that drive real-world impact and to research that not only advances knowledge but also serves our community and environment. So in closing, I want to thank all the partners and stakeholders who have made this initiative possible. Together, we are building the knowledge and tools that will help Western Australia thrive in a changing climate. Thank you, and I look forward to the discussions ahead. Thanks, Trina.
Thank you very much, Peter. Our next speaker is Mark Stickles, AM. He is the CEO of the Pawsey Supercomputing Research Centre and has been there a while, since 2018. And it says here, leading Australia's premier Tier 1 HPC, which I assume is High Performance Computing Facility. And January 2024, he was honoured to be a member of the Order of Australia for his significant service to science, especially information technology to the broader community. So he's had 30 years in the field and he's played a pivotal role in driving innovation through major national and international initiatives. So I stumbled over that a little bit, but thank you very much, Mark.
Thank you. When you said 30 years, I thought I might need to sit down again. But can everyone hear me okay? Yep. That's great. Thank you very much. Good afternoon, everyone, and thank you so much for supporting this event today. I would also like to acknowledge Auntie Mary. I had a chance to have a conversation with her before we came in, and I said, "Oh, this Wodjula knows a few words of Noongar, but I'm a bit nervous about speaking in front of you." But I got permission. I tried it out beforehand, and I'll say Nala Kadich, Noongar Mort, Kayan Karak Nijabuja. These are words and a language that's been spoken for tens of thousands of years on this country, and it's just wonderful to have you represent that knowledge and this place. We also chatted a little about this place and how we're in awe of this building. This building and what it means is wonderful, but this place and this university has also been where Marinelli was one of the first programs here to actually teach language. So for Wodjulas like me to be able to learn, but even lost language in your own community is something I just wanted to acknowledge and to thank you for. So today we celebrate the achievements of the West Australian Climate Science Initiative, and this initiative is a wonderful collaboration that stands, I think, as testament to our state's commitment to scientific excellence and partnership. And at its heart, the initiative brings together remarkable research teams and advanced technology to tackle one of the greatest problems of our time, the greatest challenges of our time, understanding and preparing for a changing climate. And at Pawsey, you've heard a little bit about us mentioned a couple of times today, at Pawsey our goal is arguably to make the invisible visible, to generate actionable insights from masses of data. And you might read later about the size of this data. So we'll talk about 8 petabytes of data. And I thought, how do I describe that to a broad audience today? It is a staggering volume. It's enough to fill 20 million 4-drawer filing cabinets. Now, some of us here are probably old enough to know what a filing cabinet is, but we know that's an awful lot of paper, or hold 500 billion pages of printed documents. And to put that another way, if you were to compare that to high-density storage that you might have in a home computer, you'd need at least 10,000 of those sort of stacked up to match the data that Professor Carla and his team and collaborators are working with. So it really is a significant data challenge. It's the scale of this that supports the world-class science that's led by Professor Carla and his colleagues from a Pawsey partner in Murdoch University, and also our collaborators in the East States and leaders in the department in DWER. So thank you for your kind words from the Director General. But to process that data, you need a powerful computer, and that's what generates the meaning and the insights from the data. And we've provided to this project more than 60 million sort of compute hours or cycles to support this system on, we say cetonics, tomato, I don't mind. Not the world's fastest marsupial, but we know it's the most endearing and uniquely recognised as a West Australian icon, and I think reflects our collaborative attitude and approach to engaging this in what we do. But if you wanted to picture cetonics, imagine tens of thousands of high-end laptops all working together non-stop 4 months on this single problem. That's the level of computational power that it takes to process this sort of data. And as I think it was referenced, and I got a nudge from the Deputy Vice Chancellor, really, but it would take a person a million years to do that. It's really hard to make the comparison, to sort of visualise and understand this, but it is something that is just not possible on a desktop. It needs a level of scale and expertise, and I do acknowledge there are several of my colleagues here in the room. Please chat to them and ask them the harder technical questions that I can't answer. We do talk a little bit about technical milestones in this project, and high performance computing is a foundation not just for this project, but it's also for a lot of decision making across society. So by building ever more detailed climate models, we do equip governments with the information that they need for water planning and disaster preparedness, to empower farmers to make decisions about crops, and having married into a farming family, I know that's an important sort of decision, but importantly to help our conservation managers adapt so that West Australia's unique biodiversity can endure. These capabilities amplify how science benefits all parts of the community. Industry leaders use these predictions to design infrastructure that will withstand future extremes. Health and emergency services plan for resilience, while regional communities access the best available information to build for tomorrow. And as we drive for higher resolution and advanced modelling, the aim is always the same: to provide robust local evidence that enables smart, fair and future-focused decisions. I also want to highlight that Cetonix and Pawsey is very committed to sustainability in every aspect of our operations. Cetonix is our flagship supercomputer, and it's ranked among the world's most energy efficient. And we achieve that through a combination of sort of cutting-edge technology, sensitive environmental design of the infrastructure and innovative cooling solutions. We've pioneered aquifer water cooling and recharge to support our systems, and it saves several million litres of water a year. We also use solar and efficient energy design and optimise the use of the system to maintain and offset our carbon footprint. These efforts help provide powerful computing capacity to drive advanced climate models and AI research, and we do this with a strong focus on minimising our environmental impact. So in today's environment of accelerating AI and increased data demand, balancing compute power with energy efficiency is more important than ever, not just for science, but for the planet that we all share. So I'll finish with a final thought. Resolution, I think we got an insight into resolution is one of the key steps in this project. Resolution in both images and in science is about clarity. The clearer our understanding of the challenges and risks ahead, the better we can work together to respond. The achievements of the Climate Science Initiative remind us that by pairing scientific ingenuity with world-class technology, Western Australia is not just observing change, but meeting it with knowledge, preparedness and collective action. Thank you.
Mark, thank you very much. So now we start to get into some of our presentations for the day. So first up, we have Dr. Paul Durack. He's the Acting Senior Manager of Climate Adaptation at DWER, and he actually completed his undergraduate degree here at Murdoch University, and then he moved east and worked at CSIRO in the Climate Risk and Resilience. Then he moved to the USA in 2011 and has been leading the development and delivery of the World Climate Research Program Coupled Model Intercomparison Project, that's a mouthful, for the last 10 years. He is the lead author in the upcoming IPCC AR7 report and has contributed, that's due for publication in 2028, and he's been an invited author in the last 2 rounds. So welcome, Paul.
So just to thank you to everyone that's introduced things at the moment. We're jumping into the science now, so thank you to very much to Annie Maria, to Alistair, to Peter and also to Mark for setting the scene. It's a pretty exciting time to come into Western Australia and to engage in this activity, which has gotten up and running a couple of years ago. And so the role that I'm going to be talking through now is just context setting, which I think most of us are on the same page, but it's a good point to reflect on. So global climate change is something that we're all very familiar with. Regional climate change is what we're trying to deal with, but this is where we stand at the moment. So on the right-hand panel, you can see the observed warming from the 1850s through to the more recent period, and there's the pronounced warming. Global average warming is around about 1.48 degrees at the end of September this year, which was the third warmest September on record after the 2 preceding years. So we've certainly got something that's pretty persistent, and it's pretty obvious when we look at the plot on the right-hand side. So 2025 is likely to be the third warmest year on record, which is another benchmark that we just keep repeating year after year. And then when we see a map of these anomalies for September 2025, we can see that this is not just like part of the globe, it's the whole globe. So both the northern hemisphere, which is coming out of summer, and the southern hemisphere in winter, everywhere you see here, there's a positive temperature anomaly, and it truly is global climate change and climate warming. So this is very unusual when considering, say, 10-year averages, thinking about climate. What we can see is that the early part of the record, the dark colours here, averaged up in 10-year or extended 40-year averages in some cases as well. And as we've proceeded through the 20th through the 21st century now, we can see that the last 3 years are actually off the charts. They're at the top here. So we're certainly dealing with global climate change. So what is driving this? Many of us know that, that human-driven climate changes are what has caused this, but this is based on climate change detection and attribution science, or DNA science, which identifies the cause and effect. And what we have here is we've got Earth system model experiments, global models that are run with experimental configurations that include and exclude the human influences. And what we have on the right-hand side here is a number of average simulation outputs for global temperature. And what you can see down the bottom here is if we run simulations that exclude human impacts, the aerosols or the natural, the blue and the green, we don't see much of a global warming. But if we run the models with greenhouse gases alone, we see this strong red warming. Or if we combine the combination of both the human and the natural causes, what we get is these grey curves. And the grey curves and the observations are very much in agreement. So without the human influences, these observed changes that we see, the black line there, are just not simulated by models, and it's very much a distinctive indicator of human-caused climate change. So a body of evidence over many decades drove the last IPCC assessment statement, which is, it is unequivocal that human influences warm the atmosphere, ocean and land. So it's very much us. Climate change is a human impact. So global climate change is something that is a concept which we're aware of, but you don't feel global climate changes, you feel local climate changes. And local climate changes are then realised through events in particular. So when we think about events that have happened in the state, the graphic on the right-hand side is extracted from the Climate Adaptation Strategy document 2023. And what we can see is these kind of events have been impacting the state from the far north to the south, all the way to the east as well. So some particular events, we've had Ningaloo bleaching, which has happened in 2021-22, and it's happening right now in 2025. And that's having a very significant impact on the ecosystem up there. We've had floods that have closed highways, the air highway closure in March 24. We've had very distinctive flooding, Fitzroy River crossing, for example, that disabled communities actually in January 23. We've had, still to date, Australia's hottest day on record of 50.7 degrees, which is an extremely hot temperature. I've never experienced that myself, but that was extreme in January 2022. And then we've had tropical cyclone impacts which have devastated some coastal communities and also bushfires as well. So this is truly something that we're living with today. It's not a theory, it's something that we're actually having to deal with right now, and we need to figure out how best to prepare ourselves for the future. So as Alistair noted, WA is considered a canary in the climate change coal mine. And what we have on the panel on the right-hand side here is time history of stream flow into the Perth Basin, effectively. And when we look at this and we look at the averages over time, we can see there's been fairly dramatic step changes in the stream flow related to the rainfall changes that have been happening in the state. But these are very, very big, and they're starting to really impact what the community does and how we operate here. So I'd note that stream flow is more sensitive to the rain amount alone. It's something that effectively has a memory in the system, so it means that we need to effectively receive a fair amount of rainfall to enable the stream flow then to run off. And what's happened is the deficit in rainfall over a considered period of time since around about 1970 is something that has seen this step change, and we've had to deal with this change real time. So if we look at the time history, for example, of these changes, you can see most of the rainfall that we receive and then the stream flow from that occurs in the winter months in May, June, July, August. And you can see at the very beginning of the century or last century, we had these fairly strong stream flows of about 400 gigalitres. In the more recent period, it has been a fraction of that, down to around about 50 gigalitres, which is an enormous drop. So it's a massive reduction in the amount of water that we have available, potable water. And even if you think about this year, 2025, as being quite a wet year, that I've returned back to Western Australia and I'm going, what's going on? There's a lot of rain. You can still see that even this year, when we've got a lot of rainfall, we've still got these incredibly low stream flows compared to what we had in the past. So climate change is here right now and we need to deal with it. So I'd note that the state has quite a track record in using science to really inform policy. And Steve Charles over on the far right-hand side there was actually involved in this Indian Ocean Climate Initiative, which was a science-driven project, which was a partnership between the Western Australian State Government, CSIRO and Bureau of Meteorology, which kicked off in the late 1990s. And it was a three-stage project, which was really trying to understand the stream flow changes and water changes that had happened in Western Australia. And what this then led to eventually was Western Australia's first desalination plant, the Kwinana plant, opening in 2006. So science-driven policy and science-driven planning was something that I think the state has a really good track record in. And the Indian Ocean Climate Initiative really set the scene through the late 1990s through to the early 2000s and into the 2010s. So where we are now. So the Climate Science Initiative builds on the past successes, developing a Western Australian climate science capability to meet Western Australian needs. We've got a really good track record of science-driven informed policy, and this is exactly what CSI is aiming for. So we're building and learning through new and continued partnerships. So the Western Australian Government, again, multi-agency, Murdoch University, Pawsey, New South Wales Department of Climate Change, Energy, Environment and Water through their NARCLIM project, which is what Alastair mentioned, and then also connections through the federal government agencies. Some of the familiar agencies there, CSIRO and Bureau of Meteorology, were involved with the IOC project back in the 1990s, and more recently now, ACS, the Australian Climate Change Service. So this is very much about leveraging latest climate data and techniques to really inform and provide information for Western Australian use. So CSI is pretty well positioned. We have a number of staff. Jatin and myself are actually invited authors on the next round of the IPCC assessment. You can see a couple of mug shots here on the right-hand side here. So the project is really pretty well positioned to be very well connected to what is happening internationally, to feed that into CSI and really inform us, going forward from this moment onwards. I've also been involved in the CMIP7, the next generation couple model planning phase, and we're expecting new simulations, these global simulations, to land early in 26 actually, and extending through 27 as well. So I think we're ready for the next round of information from Kim.
Paul, thank you very much for setting the scene. That was, it never hurts to be reminded yet again about what we're facing here in Western Australia. I'm going to bring this down because I think Kim's going to need it down. So our next speaker today is Dr. Kim Tran. She is a program manager at the Climate Science Initiative at DWER. She is also from Murdoch University and has a PhD in chemistry from here, and she's previously led climate risk assessment and disclosure reporting at DPERD. And she's managed international water and hydropower projects in Bulgaria, Bhutan, Liberia and the Philippines through her work in the Norwegian Water Resources and Energy Directorate. And she also brings extensive experience in environmental education and sustainability. So, Kim, welcome.
Good afternoon. So we listened to Paul about all the impact that we experience with climate change at the global level and also in Western Australia. So now I would like to talk, my presentation now is about, the overview of the Climate Science Initiative. So what we do, we produce the climate projections. So why are we doing the climate projection? So that Western Australians are equipped with the latest climate science and knowledge to respond to our changing climate. So we produce the high resolution climate data and information available and accessible to decision makers and the community. We encourage and empower Western Australians to use the climate data in planning and decision making, and to identify and plan the future sector and regional specific climate data and knowledge needs. So, the need for this more detailed local information is shared by all sectors across the government, communities, and business. So this slide here is show that the benefit of the climate projections to several sectors. One is, for example, the disaster risk reduction. So we know that climate change is causing more severe and frequent extreme events like bushfire, floods, and storms. So the local climate projections can help agencies like Defense, Department of Fire and Energy, Emergency Services, and local firefighters to prepare for changing bushfire patterns. And for environment, and the projection support agencies like the Department of Biodiversity, Conservation and Attraction, and Aboriginal Rangers care for country, our unique biodiversity and parks and reserves. And within the energy sector, it helps to the utilities company like Western Power to keep our power secure as the climate change, the climate become extreme, and the planning of future energy demand and prioritize the location of renewable energy project. And with agriculture, it helps the farmers to choose the crop varieties with high yield and to maximize the yield and manage the changing rainfall pattern. So what will we deliver? So as you heard before, the Climate Science Initiative received $7.35 million from the state government to work, and the timeline is from 2021 to 2027. And we produce the most detailed climate change projections ever for Western Australia, extending to 2100. We produce approximately 150 variables, and now it's available on SLIP, the Shared Location Information Platform, the 20-kilometer statewide data set, and the future, very soon, hopefully in early 26, we will have the 4 kilometers grid cover the southwest of Western Australia, and by the end of 2026, we will have the northwest of Western Australia. And for the communication products, we are in the process of procure the interaction climate change projection viewer. So hopefully that we will have everything in place by the end of 26. And we produce fact sheets, summaries, infographics, webinar, and regular newsletter. And our communication officer, Julia, will talk more about this. And regarding science and their scientific papers, research, and collaborative project. So the climate projection produced by the CSI provide a critical foundation for impact assessment and additional studies by specialized experts and through collaboration across multiple sectors. In this slide here, I'd like to introduce our project team. So from the Department of Water and Environmental Regulation, there's Dr. Paul Durack, that you just listened to his presentation just now, and myself, and Julia Oliver. She's the Climate Science Communication Officer. Our science team includes Dr. Sean Lam. He's the Principal Climate Modeler. Dr. Omer Mughal, he's the Senior Climate Modeler. And Dr. Mark Marinelli, he's the Senior Data Engineer. And from our partner institute from Murdoch University, we have Associate Professor Jatin, he's the lead scientist. And Dr. Julia Andrys, she's a senior postdoc. Dr. Jatin, she's a postdoc. And it's very important to build up the capacity of the younger generation. And so the program sponsors 2 PhD students. And their work will be presented by Professor Kagla in his presentation after this. So, with the Climate Science Initiative overview, there are 3 emission scenarios. So we use the low emission, the intermediate emission, and the high emission. So this scale of modeling has never been done before in Western Australia. So we do, first, sorry, the pointer is not working. Yeah, so the first is the 4 kilometers of the southwest, and then the 4 kilometers of the northwest. So what we have here is the 20 kilometers data product. So it's now live on SLIP at Glengate. So we have the maximum temperature bias corrected, the minimum temperature bias corrected, the rainfall bias corrected, and various statistics for each of variables are available, cover the entire state at 20 kilometer grid for technical users. And then, so we will find out more about this in the presentation of Dr. Marinelli and Dr. Sean Lam. So now it just gives you an update time frame of our program. So the SLIP data, the 20 kilometers projections, is out now, and you get information about the temperature and the rainfall. And the southwest 4 kilometers will be available in early 2026. And this has 3 emission scenarios. And scientific paper publication will be done in the 2nd quarter and the 3rd quarter of 2026. And the future climate projection viewer, it will be launching at the end of 2026. And then we have the northwest of 4 kilometers projection, and that will be complete at the end of, in the late 2026. And we have the communication products, including frequent asked questions, fact sheets, summary data, newsletter update, and this is iterative. Thank you.
Thank you very much, Kim. So now we're going to have a couple of presentations from the Murdoch team, and Jatin has asked me that I introduce them together. I think the talk flows one from one to the other. So, Jatin's been mentioned quite a few times today, so I probably don't have to say a lot, but he's a professor in atmospheric science here at Murdoch University, and his area of research expertise is the regional climate modelling and land atmospheric interactions, and we have seen he's been involved in the most recent IPCC, and I think this is becoming something that he's really well known for internationally as well. One of the postdocs from the project, Dr. Julia Andrys, will be also speaking today. Her area of expertise is regional climate modelling, and she's been involved in the initiative since it started. She's particularly interested in how to use regional climate modelling to understand how climate change will manifest at local scales and in the application to regional climate modelling data in other research fields, for example, agriculture, forestry or renewable energy resources. So how do you take that information and use it? Welcome. Thank you.
Alrighty. Thank you, Trina, and thank you to all of the speakers before me for setting the scene. So me and Julia are just gonna go straight into the science, what we've been doing and what it means. So just a bit of an overview. So I'm just gonna remind everyone about key elements of the project, what we are doing and why. Of course, all models are wrong. Some are more useful than others. To find out how useful our model is, we need to compare it against real observations. So that will be a key part of my talk today. Once we know some of the errors in the model, we can then confidently look at the future. I will also talk a bit about bias correction. So Kim, in her talk, talked about bias-corrected temperature and precipitation. I want to explain exactly what that is and why bias-corrected data actually exists. I'm going to talk a bit about other metrics we're working on using this data set. That includes various hazard metrics, drought indices, fire weather indices, and so forth. And I'm going to showcase some of the science that we're already doing with the data that we're producing. That's mostly projects led by students. And there's also other projects happening on the sidelines that are strongly linked to the CSI. And I'm going to talk a bit about that as well. Okay, what is the CSI about? As has already been explained, we will produce the highest possible future climate projections for the southwest of Western Australia. We're going to refer to it as SWWA from now on, and the northwest and WWA, right? What happens in the future at 4 kilometers? I just want to remind everyone that we did a project launch in mid-2023 that has a lot of the background. Although I'm going to cover a bit of the background today, I can't cover everything. So please have a look at the previous lectures we've recorded. Okay, 4 kilometer resolution. Why 4 kilometers? You know, why not 8? Why not 20? So if you look at this plot here, on the left-hand side is the topography, so height above sea level, in one of the global climate models that we've downscaled. That particular model is the Access ESM 1.5 model. Access is the Australian global climate model. Now, if on that plot here, if I remove the coastline, you would be hard-pressed to know which region of the world we are in, right? You wouldn't be able to tell this is necessarily the southwest of Western Australia, right? So that's how land is represented over southwest WA in these global models. It's very pixelated because these models have fairly coarse resolutions. Now, this is the topography, right, in the 4 kilometer model that we're running. And if I remove the coastline and remove the latitudes and the longitudes on the axes, you would probably you would have a pretty good chance of guessing that this is the southwest of Western Australia. You can see the Darling Scarp here along the coast, right? That sharp elevation going from close to sea level, going up to about 300 meters, right? So we can see that the regional model represents the real world a lot better as we know it. Now, we are downscaling like these global models. They're often called GCMs, global climate models. Turns out there's about 60 of these things, right? Developed by all different government agencies around the world. We can't use all of them, we can't downscale all of them. So how did we pick which ones we're going to downscale? Turns out with the resources we have, we can downscale about 5 of them. So in this paper by DWER et al., they looked at all of the latest global climate models. So that's the CMIP-6 global models that, and Paul referred to CMIP, is the coupled model intercomparison project, right? So we picked 5 out of the 60. Of course, first we said, well, these models have to simulate the climate over the whole of Australia reasonably well. If they do, are they statistically independent? What does that mean? You don't want to choose 5 models that give you the same answer, because when you downscale them, you'll get more or less the same signal. We want to choose models that are skillful, but have different types of futures. The models also must have produced sufficient data that we can actually downscale these models. Just because a global model exists doesn't mean you can just downscale it like that. It depends on what they saved. And we also had to pick models that simulated a range of future climate scenarios. Right now, what are these climate scenarios? As Kim mentioned, there's 3 of them, SSP1 2.6. Is generally referred to as a fairly low emission scenario. Under SSP1 2.6, global warming by 2100 is expected to be around 1.8 degrees. So that's warming average across the globe. And the range around that is 1.3 to 2.4 degrees. SSP2 4.5 is an intermediate emission scenario, and SSP3 7.0 is what we call a high emission scenario. All I want you to remember is going from SSP1 to SSP3, we are going from SSP1 to SSP3, we're emitting more and more greenhouse gases into the atmosphere. Now, we've got the models, we know they have all of the scenarios. How do we pick 5 of them? Now, this very complicated graph here from the DWER et al. Paper did exactly that. What I want you to get from this graph is that these are all model names, and all of these models do a fairly reasonable job at simulating Australian climate. The reason we've circled 5 specific models is that these circles, as you will see, are further apart from each other. They're not clumped. When a model is at the top here and in the middle, that's the UK ESM model. That means that that particular global model over Australia simulates a lot of warming, right? At the top here, it means it simulates a lot of warming. That's the mean temperature change. But the change in precipitation across the whole country is close to 0. If you go on the left-hand side, these are models that still have warming, but the mean precipitation change is negative. So these are warm models that have a dry future. And if you look at this model here, you see a free veg. This is a model that simulates some amount of warming, but has a wet future, right? So that's the reason we picked these models. We picked one that has quite high levels of warming, but small changes in precipitation. The Access ESM model, that's the Australian model, also has high warming, but a very dry future. The No ESM model, which we picked, has the lowest warming out of the 5 models and a dry future and the other 2. MPI ESM 2LR and ECA free veg are both have slight levels of global warming, but than no ESM, but MPISM has a wet future, and ECF free veg has a very wet future. So by simulating these 5 models, they all have reasonable scale over Australia, but they all tell us a different story as to what might happen in the future. So that's why this is important. So we downscale these models over the historical period, that's 1950 to 2015. And the future scenarios, SSP 1.2.6, SSP 2.4.5, and SSP 3.7.0 go from 2015 to 2100. Now you're probably all thinking, hello, we're in the year 2025. Okay. The reason in these simulations that the future starts in 2015 is because this is from the CMIP 6 round of climate modeling. At the time that all the climate modeling groups started running these models around the globe, it was already 10 years from now. It takes a lot of time and effort to run these models. So when the CMIP 6 simulations were released, the future started in 2015. Okay, that's the reason why it's like that. Okay, so other than dynamically downscaling these CMIP 6 global models that tell us about the past and the future under different future scenarios, we've also dynamically downscaled ERA 5 reanalysis. Now, ERA 5 reanalysis has a pretty high resolution. It's around 30 kilometers, so it's much higher than global models. So we also downscaled that to 4 kilometers. Why do we do that? Now, we downscale a reanalysis alongside CMIP 6 models because reanalyses are created by assimilating observations into numerical weather prediction models. So what happens is people try to simulate this week's weather, right? This week's weather actually happens. We have measurements of what happened from satellites, from weather stations, from weather balloons, right? What they then do is they say, okay, this is what the model simulated. This is what happened in the real world. Let's combine these two things together so we have the best possible estimate of what was happening in the atmosphere at that exact point in time. By definition, because of the way these reanalysis data sets are produced, that information is only available in the past because we don't have observations of the future, right? This is covered in detail in the project launch lectures, so you can find out more about that. So how does it work? Okay, so we have these global models or reanalyses. They cover the whole globe, right? But the resolution is not sufficient. What we do is we take the data over the region of interest and we use that as input into a regional model. Now, the way the maths and the physics turns out is that you can't possibly go to 150, 250 kilometers to 4 kilometers in one shot. The math will break down, the physics doesn't work. We have to do it in at least 2 steps. So first of all, we go to a 20-kilometer resolution. That 20-kilometer resolution is what is commonly referred to as the Codex Australasia domain. It covers Australia, New Zealand, and more, and that's 20 kilometers. Now, that 20-kilometer data, that simulation, is produced by our colleagues in the New South Wales government, the NARCLIM project. They take the global model, produce a simulation at 20 kilometers, and of course, because they are the New South Wales government, their 4-kilometer domain is over New South Wales, right? Now, we wanted to do the same thing, but we wanted to reach 4-kilometer resolution over Western Australia. Now, rather than go and repeat the 20-kilometer simulation and then produce the 4-kilometer simulation, they've already done the grunt of the work. So via partnership, we take the data from them, their 20-kilometer data, and then from the 20-kilometer data, we produce the 4-kilometer data, right? So we are being efficient with our time and resources. Okay, so how do we do that? That regional climate model that we use is called the Weather Research and Forecasting Model. We use version 4. WRF is developed from the National Center for Atmospheric Research in the US. The reason we use this model is that it's completely open source. Anyone in the world can use it. It's been used a lot in Australia and internationally. Because it is open source and free, lots of people use it. And things which are free and are used by lots of people are very robust because you find the problems very quickly. It's quite well documented. Now, any model, any climate model, it's not the sort of thing that comes, you download the software and you just go plug and play. They're very complicated to set up. Now, the weather research and forecasting model, you can't just go and plug and play. You have to configure it. And there's an infinite number of ways in which you can configure that model. Now, to configure it to suit our needs, what we did is we conducted a whole bunch of sensitivity tests using that model, and these tests covered the whole of Australia. We tested many model configurations, and we came up with 2 configurations we thought worked the best. They are called R3 and R5. So when I refer to R3 and R5, they're just 2 configurations of that model that we used. How do they differ? They are identical, except that they differ by the choice of what we call the planetary boundary layer scheme used in the model. The planetary boundary layer matters because it's the lowest level in Earth's atmosphere where we live, where all of the weather happens, where all of the impact happens, right? So that's why that particular part of the Earth system is critical. So we have 2 simulations each for each of the 5 global models we've downscaled and ERA 5 reanalysis. One thing I do need to note is that the weather research and forecasting model, like most regional climate models, does not have a dynamic ocean. It has a dynamic land scheme, it has a dynamic atmosphere, but it doesn't have a dynamic ocean. Sea surface temperatures from the global model, right, are interpolated to the regional climate model domain and provided as an input every 6 hours of the model run as the model operates. This is very common, whilst there are regional models out there that have dynamic ocean and dynamic atmosphere and dynamic land. Having a dynamic ocean complicates things and uses a lot more computational power, and it doesn't always make your simulations better. And the models that are being used by the Bureau and the CSIRO also have the same limitation. They don't use a dynamic ocean. The CSIRO has done some simulations, not all of them, a few, where they have activated a dynamic ocean. So that's important to know. So okay, this is the modeling. Now we need to know what is the skill of the model. How do we do that? We need to evaluate the models, and we need to choose a time period. So we chose the period 1980 to 2014 because it's the common period between the ERA 5 reanalysis driven simulations. This starts from 1980 and then in 2020, and the CIMIX 6 model simulations that start in 1950. Right, so 1980 to 2015 is their common period, so we can look at all of the model runs all together. Also, the observational data sets that we use, so we use the Australian Gridded Climate Dataset called AGCD, version 2. What is it? AGCD basically is an interpolation of all the weather stations in Australia. So the Bureau of Meteorology operates thousands of weather stations across the country. They take data from all of the weather stations, they quality control the data, and then they interpolate it over a common grid that's 5 by 5 kilometers. And that data provides us with daily precipitation, daily maximum and minimum temperature, and that data is the most widely used observational product using by all Australian climate studies. The other thing, as you might be aware, is that the quality of observations as we go backwards in time declines, right? Another reason for sticking to 1980 to 2020 is because we have much better data from the 1980s onwards. So due to time constraints, right, for this talk, I'm mostly going to focus on winter, June, July, August precipitation, because as the previous speakers have already mentioned, this is where we see most of the impact in terms of rainfall decline and subsequent decline in stream flow. Okay, so what I'm showing here on this plot is the June, July, August, so that's winter. PR at the top there stands for precipitation, and it's the climatology from 1980 to 2014 average. The top plot, hold on, oops, I've lost my, the top plot where I have the circle is the AGCD data. That's the real world, right? That's the real world there. And you can see, as we expect, red is high precip in this plot. Most of the high precipitation is along the southwest coast, and it decreases very rapidly as we go inland. So we have a west-east gradient and also a north-south gradient. Now, if you just took the global climate models, including ERA5, in their native resolution, you would get the second row, right? Now, if you look carefully at these models, you will see, as we expect, they're very blocky. That's because of their simulation. But you can see if you focus along the coast, right, and you focus on the land grid points in these models, none of them are able to simulate the very high precipitation we clearly observe in the observations, right? And to be fair to these models, they could not possibly simulate that because their resolution is very coarse. And these models, these GCMs, they were designed to simulate what's happening across the globe, not in a small specific region of the Earth. Now, we take these global models and we go to 20 kilometers. That's the third row. You can see that we've improved the simulations by quite a bit, but it's actually not improved all that much, right? You can see that on the 20-kilometer row, there's no red, and there's very little yellow. That means that these simulations, even at 20 kilometers, are not quite getting the high rainfall events. Now, we take the 20-kilometer data, we further downscale it to 4 kilometers. You can see that now we are starting to simulate precipitation magnitudes that are now becoming quite close to what we observe in the real world. So that's the whole reason for doing all of this work, is so we can come up with something like that. Okay, now for the rest of this talk, I'm going to only focus on the 4-kilometer data. Now remember, previously I said we had two model configurations, R3 and R5. What I've shown you here is the average of the two. Now, what I'm going to show next is how these two model configurations differ as compared to the observations. So we're now going to compare, in the next slide, these simulations, right, in the last row to the real world in more detail. So what is shown here is what we call the bias. Bias simply means model minus observations. If model minus observations is positive for precip, it means the model rains too much. If it's negative, it rains too little. What you will see here is that all of these plots more or less have blue along the southwest coast. That means that all of these models, and these are all the R3 configuration, they simulate a bit too much precipitation. Where you're seeing the hashed lines, that's called stippling. Where there's the stippling, it means that when we do a statistical significance test, that test tells us that the bias is statistically significant. So we should care about that bias and the magnitude of it. right? And when we average all of the R3 configurations, you get the plot at the bottom here, which is the ensemble mean of all of the R3 configurations. You can see that overall it's blue along the southwest coast. So the R3 model turns out, whilst it is much better, the 4 kilometer data was much better than the 20 kilometer, was much better than the global models, still has errors in it, as we expect. Now, if we look at the R5 configuration, right, these are the red circles, you will see that some have a bit of blue, but most have a bit of red and yellow. That configuration of our regional model tends to simulate, for quite a few of the models, a bit too little precipitation. When you take the average of all of them, you get the plot at the bottom there, right? So we have two model configurations. Again, models are not perfect. We expect them to have errors. One runs a little bit too wet, one runs slightly dry. And that's a good problem to have. If we did this, and both configurations were always too wet and both were always too dry, it would not be a good outcome. To have models that differ in their errors is a good thing. Now, of course, the next thing we asked ourselves, why is it that the R3 configuration of the regional model produces more precipitation than the R5 configuration? This is what we are showing here. This is R3 minus R5, right? So the model that rains a lot more. The difference in precipitation, that's the top row. So it's all in blue. That means that the R3 model simulates too much rain, a lot more rain than R5. Why does it simulate a lot more rain than R5? It's because what is shown on the bottom plot here is because it simulates a lot higher what we call convective available potential energy, CAPE. I know that's a mouthful, but all it means is the amount of energy available in the atmosphere to generate convection, to push air up so it condenses out, forms clouds, and it rains. So we understand why these two model simulations differ in how they simulate precipitation. We also looked at regional averages. So what we've done here is we've taken the southwest region and we've subdivided it into 3 regions that we broadly call the Swan Coastal Plain area. So that's the high rainfall area. In the yellow bit is more or less the wheat belt, and in the brown bit is what we call the rangelands. So we looked at the seasonal cycle of precipitation. So what you're seeing on this plot is January to December rainfall. So if we focus on the southwest coastal region, that's where we get the highest precip. That's on the top row here. This is the R3 configuration, right? The R5 in the middle and the average of the two on the right-hand side. What I'll point your attention to here is the dotted black line is the AGCD. That's the observations, so you can very clearly see, the seasonal cycle. We know all too well here that it buckets down with rain around June, July, August, right? So in R3, most of the models are a bit too wet. In R5, it's a bit better. And when we take the average of the two, overall, we have a model that performs reasonably well. And now, if we focus on what's happening in the wheat belt, of course, as you move further inland, the rain decreases drastically. So you will see that the observed seasonal cycle in the dotted line doesn't peak as high as close to the coast, which we expect. But overall, the model does a pretty job of reproducing that cycle. In the rangelands region, that's going a lot further inland, we do not have that cycle, right? Because as you go a lot more inland, the rain becomes a lot more sporadic, a lot more difficult to simulate. But overall, we can see that our model simulations do a pretty good job. Okay, so to summarize what's going on, right? The global models in their native resolution do not simulate precipitation in the southwest very well. We know they have this limitation. We downscale these models to 20 kilometers it improved things a lot, but not enough. Further downscaling from 20 kilometers to 4 kilometers, what we call convection permitting, makes a big improvement. And if you think about this, if you look outside and you look at clouds, and you look at the area that's covered by a cloud, that area is fairly small, right? In a 20-kilometer regional climate model, there's a 20-kilometer box, and we're trying to simulate everything that's happening in that box. Within a 20 by 20 kilometer area, you're going to have many small clouds, not one cloud, right? When you go from 20 to 4, suddenly we can simulate convection a lot better, which is why we see a lot more rainfall in these simulations. Now, even these 4-kilometer simulations, they have biases, right? R3 is a bit too wet, R5 is a bit too dry. This is a good thing, right? So we have carried out the analysis over all of the seasons. We have looked at maximum and minimum temperature and also other climate extremes, right? So I can't, due to time limitations, I'm not going to be able to present all of that, but our model does pretty well. Now that we know something about the skill of the model, you're probably wondering, well, what does the future look like? So for this part of the talk, I will tag team to my colleague Julia, and she will talk about what the future looks like in all of these simulations.
Hi everyone. I think I get to talk about the best bit at the moment, and that is the climate change signal analysis that we have worked on so far. So before I go in and start showing you some plots, I just want to give you a bit of some information on how we calculate the climate change signals. So in the analysis I'm going to show you in the coming slides, we look at 3 different periods. We look at a baseline period. In this example, we're looking at 1981 to 2010. Then we have a near future period, which is 2031 to 2060. And then finally, we have our far future period, which is 2071 through to the end of our analysis in 2100. That climate change signal is calculated, it's the future period minus our baseline period. And obviously I've got some asterisks there. The baseline period, we've considered a lot of different periods. We could have taken, for example, 1951 through to 1980. That would have given us a stronger anthropogenic signal. Another baseline period which is commonly taken is 1961 through to 1990, which, as Jatin mentioned, that's when the observational record sort of really starts to have we have a lot of confidence in that. But for this particular example, 1981 to 2010, it's sort of more recent climate that we have, so it's just what we've chosen to do this particular analysis with. Okay, so this is the ensemble mean climate change signal for precipitation. So I've got a lot to sort of talk you through on this slide, so just sort of bear with me. On the left-hand side here, these 9 plots show the near future, and then on the right-hand side, we're looking at the far future data. On the top line, we're looking at our low emission scenario. The middle line is our intermediate emission scenario, followed by the high scenario at the end. I'm going to talk a little bit about summer climate change here, but you can see that what we don't really have is a very strong signal. We've got a little bit of drying, a little bit of wetting, but there's not really a lot of movement either way. So, and you can also see in the means there, there's not really a lot of change. But as Jatin's focused on the winter precipitation, you can see that we do start to get this progression from the near future as we move to a higher emission scenario, and then of course as we move into the far future, you do start to see that drying signal, and it does start to increase as we move into the far future and as we increase our emission scenario. Now there is dots. This is the stippling that we've used here. What that stippling here is representing is this data I'm showing you is an average of our 10 simulations that we've run for each of these different scenarios. And in these 10 simulations, for that stippling to occur there, each model, the majority of the models had to be statistically significant. So the climate change signal had to be statistically significant, and the models had to agree on the direction of the change. So it had to be a drying signal. So where you see the dots, what that means is we are pretty confident in the data that we've generated that signal is in fact what we would expect to see. So I'm just highlighting this box here. This is our high emission scenario for winter in the far future. And what we're going to do is we're going to have a look under the hood here, and I'm going to show you in this slide These are the ensemble members. So these are the climate change signals for each of the 10 ensemble members and what they look like. And that's sort of how we got that ensemble mean. So you can see that in a couple of the models, which is our EC Earth model and our UK ESM model, you can see we have wetting in the rangelands and interior region. But overwhelmingly what you see is we have this very strong drying in that southwest region. So that's in the region which we call the Swan Coastal Plain, moving also into the Wheatbelt area. Now, as Jatin mentioned in his previous slides, when we chose these 5 GCMs, we chose from the whole range of climate change signals. So we made sure that we had some wetter futures, we had some drier futures, and all these models also had that level of independence. But you can see that despite the fact that some of these models were wetter and some of these models are drier, or predicting wetter or drier futures, there is consistency in this southwest region, and they're basically all saying, yes, we have a drying signal, and that drying signal is significant. So as far as what our data is showing, there is a lot of consistency. There is a pretty reasonable degree of confidence that we are going to see that drying pattern. Okay, so this is just looking at that data in a slightly different way. This is time series anomalies. And what we've done here is we've just broken it down into the different regions. So here in the Swan Coastal Plain region, what we see is we've done a time series, we've patched our historical simulations, and then on the right-hand side, we're moving into our low, medium, and high emission scenarios. The low is in green, and the medium is blue, and the high emission scenario is in red. So one of the things that to me is immediately apparent here, I'm not sure if you can see, we're looking at our far future period. So you can see it sort of starts about there. And this is really where our medium and high emission scenarios do start to sort of diverge from the low emission scenario. You can see that under the low emission scenario moving forward into that 2070 to 2100 period, you still have these decent peaks of high rainfall years. But you can certainly notice that as you move into the medium and the high emission scenarios, those peaks of variability that we tend to see in the southwest region, they are really diminishing quite a lot. You can see a sort of similar pattern in the Wheatbelt region. Obviously, the anomalies are lower because the rainfall is lower generally, but you do also see that divergence from about 2070 moving forward. And down here, this is looking at the rangeland region, and obviously, as you saw from Jatin's slides previously, there's not a lot of rainfall in the winter period in that rangeland region, so we're not seeing a lot of variability there. What that basically means is, we can't really unpack much from a climate change signal looking at seasonal rainfall in winter in that region. But obviously, we've got a lot of information in the Wheatbelt and the Swan Coastal Plain. Okay, so we wanted to look at other aspects of rainfall, because it's not necessarily just the amount of rainfall, as Paul mentioned in his presentation. There's a lot of other factors that influence how the rain interacts with the ecology in WA. So what we wanted to look at here is the winter rainfall contribution from consecutive rain day episodes. So we based this analysis on a paper from Day et al. And what they did is they analysed this episodic rainfall events from the observational record. So we've tried to take their analysis and sort of, in the coming slides I'll show you, we've applied that, and we've had a look at their results. Found that in the observational record there was a reduction in, rainfall was becoming more sporadic. So we've just tried to project that forward. So just to give you an idea of what we're looking at here, we're defining a rain day event as a day where you have more than 2 millimetres of rainfall. So when I'm looking at these 7-day rainfall events, that doesn't mean that it's rained continuously for 7 days. What it means is we've had 7 days in a row which have had greater than 2 millimetres of rainfall. And from here, what we can see is over most of our region, most of the rain, up to 100% in the rangelands and in a lot of the Wheatbelt, comes from 1 to 2 day rain events. But you do see that at 7-day rain events, we do get a significant contribution from 7-day rain events. And in the Wheatbelt, that's up to 50%, 40% in some cases. So what we've then done is we've then looked at the contributions in our forward projection. And so here I'm looking at the SSP. So this is the high emission scenario for the far future. And this is ensemble mean data that I'm showing you here. So what our simulations are doing is we are projecting in the future that rainfall is going to become even more sporadic. And how we can sort of interpret that is, so we're going to get a greater rainfall contribution. So we're going to get up to a 10% increase in rainfall from 1 to 2 day rain events. And commensurate with that, we're going to get approximately a 10% reduction in rainfall that's coming from these 7 day or week-long or more rain day events. There's not sort of too much to unpack with respect to 3 to 4 and 5 to 6 day rain events, but there is that really significant switch between 1 to 2 day and week-long rain events that we are seeing here. You may also have the question, if you've been paying attention, about the stippling, and the reason why there's no stippling or dots on this plot is I simply did not get around to sort of checking that. So this is preliminary analysis. So that doesn't mean that there is no significance there. It just means that that's not something that we have gotten to yet. We talked a lot about rainfall. And obviously that's because it's quite important, but I did want to just very quickly just give you some information on the climate change signal with respect to maximum and also minimum temperatures in some coming slides. So again, on the left-hand side, you're looking at your near future. Your right-hand side is your far future, and then your low, medium, and high emission scenarios. So again, you can see here that we do have this progression as we move from the low to high emission scenario and as we move from the near future to the far future. You will also note that here, everything is stippled. There's dots everywhere. What that means is that all the models agree that there is warming and all the models agree in the direction. So, you know, there's a high degree of confidence there. In terms of what are we showing you here that is different to what you would get from a GCM, well, the magnitudes of the increases are about the same, but what we are revealing here is we are seeing about half a degree warmer on average in the southwest in the summer compared to the winter period. And it is also interesting that this is what we get from our 4 kilometre data here. If you can see, there is quite a lot of spatial variation in the warming that we are seeing in the southwest. And this is what we're able to capture with this 4 kilometre data. You know, in particular, I'm not sure if you guys can sort of get an idea of that, but you know, there is that you know, intriguing patch of warming sort of over that Swan coastal plain and into that Swan catchment area, which is something that, you know, from my perspective, very interested to unpack. And, you know, hopefully the information that we provide to you guys on that as well is valuable. We're just going to have a quick look at minimum temperatures as well, because the minimum temperature data is important in terms of from agricultural applications, but it's also important in terms of when you look at heat waves and how we perceive a heat wave, in terms of if you have very warm nights, then, you know, it's a contributing factor towards how we calculate heat waves. So again, near future on the left-hand side, far future on the right-hand side, and we see that progression in warming. What you do see as well is minimum temperatures have, it's warming faster in summer than it is in winter. And you do get, again, some really interesting spatial patterns with respect to, there's a bit of a spatial pattern there with respect to land use, because you can sort of see that wheat belt area, and there is a slightly reduced warming in the wheat belt area compared to the rangelands where that warming is increased. So, you know, from my science perspective there, that's interesting things for us to unpack and discover why the models are providing us these spatial patterns. Okay, so before I hand back to Jatin, I'm just going to give you a quick summary of you know, what we've talked about with respect to the climate change signals. The rainfall simulations really are showing us the most added value compared to what we're seeing from the GCM simulations. I think Jatin's highlighted a few slides there, and, you know, we've shown you that sort of that real spatial granularity that we are seeing in our models. But there are also some interesting spatial patterns in the temperature climate change signals as well, and I hope I've highlighted that because I think that they're pretty interesting as well. As we expand our analysis to include more climate extremes, things like hazard indices, sub-daily data for rainfall, when we look at things like intensity and so forth, we really expect that the added value from our 4 kilometre convection permitting data will become more apparent. And just wanted to just reiterate, this is a very, very brief snapshot of our current analysis. I'd love to spend time talking to you guys about it even more, but I know you guys do want to get home at some stage today. And so we are working on a manuscript with this data, and we look forward to sharing that with you guys in the near future. And I'm going to hand back to Jatin now so he can finish his talk. Thank you.
Thank you, Julia. Now, to finish this talk, I want to talk a bit more about how to use the data and what to consider. So we have simulations that are driven by ERA5 reanalysis and these CMIP6 models. So the ERA5 driven simulations are only limited from 1980 to present. As I explained, that's because ERA5 is a reanalysis that assimilates observations, and hence we can't use that to tell us about the future. So this data set is very useful when you're only interested in what happened in the past. The reason why we run this ERA5 driven simulation is because it acts as a benchmark. Broadly speaking, we expect a reanalysis data set such as ERA5 to perform better than a CMIP6 global model because a reanalysis assimilates observations, a CMIP6 model does not, right? So we strongly recommend, if you want to use this data, to first use the ERA5 driven simulations to get a feel for the model, understand some of the errors and biases in the model before you go into the CMIP6 driven simulations. The CMIP6 driven simulations, right, provide both the historical period, so that's 1950 to 2014, and the future scenarios 2015 to 2100 under the three different future climate scenarios, SSP1 2.6, SSP2 4.5, SSP3 7.0. With these simulations, we typically are looking at 30-year averages, right? We are trying to look at what happens to the statistics of the climate system. The completely incorrect way to use this data that will get me very riled up is to say, I really would like to know what will happen on the 15th of January 2051 on the Murdoch camp. This is not what this is for, right? You must only use and only focus on the changes in the long term, right? Climate is the aggregation of weather events. We encourage you to use all the projections and not just the ensemble mean. An ensemble mean simply means averaging out all of the models. Ensemble means are useful to paint the big picture, but the world, people, ecosystems do not respond to an ensemble mean. They respond to a shift, right? So it is important. The reason we run 5 models under 2 model configurations is because we want people to use all of it, right? Now, as I've shown, right, all models have errors, right? We have quantified the errors in our model. That is what every climate scientist worth their money, that's the first thing they do is figure out the biases in my model. All models have biases to some extent. Now, these biases, you perhaps can live with them, maybe you can't, right? There are many instances whereby the biases in the model, you have to do something about them before you use the data. For example, maybe you're a health researcher or an ecosystem researcher, 40 degrees matters to you. You want to look at the number of days above 40 degrees. Now, well, we know these models have biases. So if a model that is a bit too warm, right, generally will have too many days above 40 degrees, right? So you can't look at the number of days above 40 degrees and say, this is what's going to happen in the future, because it's going to be different between different models because they all have biases of different magnitudes. Now, this is where bias correction comes in, right? Now, something else people want to do is to use the output from our model, for example, precipitation, and use that as input to other models, for example, to predict stream flow, right? Now, if you're going to do that, you need to take into consideration the bias in the model. The way we do that is by using bias correction. Now, what is bias correction? All models have biases. These biases can be corrected in a statistical method, right? So we do have observations of some variables, so we know what the error is. If we know what the error is, we can remove that error, right, To quantify that error, we should have good observations, so usually it's limited to temperature and precipitation. Bias correction can also be applied against some reanalysis data set that we trust enough. So for example, in Australia, we have pretty good observations of temperature and rainfall from the AGCD data set that I presented before, but there is no equivalent for wind speed and wind direction, right? So then what people sometimes do, they say, okay, there's this other high-resolution reanalysis product. I understand a reanalysis is still a model, but because it assimilates observations, I trust it more. Therefore, you can bias correct your winds against other reanalysis data sets. So all of these things can be done, and we're going to do them, but I also want to point out that we cannot bias correct everything. A typical example is soil moisture and soil temperature is almost impossible to bias correct against. Why? Firstly, there's very, very little soil moisture observations. You can get it from satellites, but usually it's at the surface. If you're interested in soil moisture, 10 centimeters within the ground, 20 centimeters within the ground, it's very difficult. Even reanalysis data sets have very unreliable soil moisture and soil temperature. So it is important to know that you can't bias correct everything. So now, how does bias correction work? So you can have, this is a purely for illustrative example, right? Say this is the temperature distribution from a model in blue, and the temperature distribution from the observations is in black. So clearly, in this instance, the model has too wide a distribution, and its peak is too high. It's over-predicting temperatures. So what we can do is we can say, okay, let's develop a statistical relationship between the historical observed data and the climate model data over the same period that we have the observations for. We assume then that this error stays the same as we go in the future. We have no other choice, right? So if we can reasonably assume that the relationship between these variables does not change into the future, we can then apply this bias correction method to both the historical data and the future projections. There are limitations for that, right? Bias correction works for the means. It doesn't work very well for extreme events. Why does it not work very well for extreme events? Because they are rare. We don't have lots of observations of them. It's very hard to quantify errors in extreme events because they are rare, not a lot of observations. But it can still be done. So this is an example of bias correction applied to the New South Wales 4-kilometer data from the New South Wales government. That's from the NARCLIM 2 project. And these slides have been provided by our colleagues in New South Wales. This is on the left-hand side here. AGCD is the observations. DJF is December, January, February. That's summer precipitation over the East Coast. And these plots here are all the simulations, and these are the biases. So this is model minus observations, where it's dark brown. It means that the model is too dry. Where it's dark green, it means that the model is too wet. So that's no bias correction. And then they apply the bias correction, and what's happened. So for example, if you look carefully, right, that's the Access ESM 1.5 model of reconfiguration. That model over the East Coast produces too much precip along the coast. After they apply bias correction, that overprediction is gone, but you will also notice that there's now more brown, right? This is what we have to live with, right? There's no magic trick here. What's happened is that, yes, we've removed a significant wet bias, but we've also made dry biases a little bit worse, right? This is another example here where they've bias corrected the ECF free veg model. You can see we've removed a lot of the errors, and then in the ECF, in the R5 configuration, a lot of the dry bias has been removed, right? So these things can be done. So we have started work towards bias correction of the CSI data. We plan to use the same method used by our New South Wales colleagues. As it turns out, our federal colleagues are using a different method called the quantile mapping method. We will also apply that same method so we are consistent with the national projections. Our team is currently working on getting that code to run on Cetronics. So we're aiming for around the first quarter to mid-2026. This data is recommended if you're going to look at absolute thresholds or you're going to use the data as input to other models. Right, so we've run the model and we've produced a lot of data. Now, what variables we produced, there's a lot of them. Now, as it turns out, there's something called the Coordinated Regional Climate Downscaling Experiment Codex. Is an international organization that tries to coordinate between all of the regional climate modeling groups across the globe. So Codex has come up with a bunch of variables that all of the groups, like ours, have been requested to produce. These are variables that the list that they've come up with is a list that they've come up with after a lot of stakeholder engagement. These are the variables most people are after. There's way too many of them for me to list all of them, but they are called Codex Core. This is what most people want. That's your temperature, precip, humidity, surface heat fluxes, and tier 1 and tier 2 variables that are usually of more interest to people who do atmospheric dynamics and so forth. There's a full list that you can look at on this page. We have computed already the vast majority of these variables. They've been produced. They are sitting on the Pawsey storage system. There are also other metrics that are very useful. So there's an international group called the Expert Team on Climate Change Detection and Indices, ETCCDI. If you follow that link, it will send you to a website where there's a whole bunch of different climate indices that people are usually interested in. That includes things such as consecutive wet days, consecutive dry days, rainfall exceeding the 95th percentile of precipitation, a whole bunch of extreme indices. So we are working towards calculating all of these. In Australia, we use the MacArthur Forest Fire Danger Index. There are other indices as well that relate to fire weather. So we're calculating that and other indices. There's other indices that are related to storms and hail events. Drought metrics, some of you may have used or heard of the Standardized Precipitation Index. And I'm going to show some results about that shortly. Drought duration, frequency, intensity. We also calculate a whole bunch of heat wave indices, heat wave frequency, duration, intensity, magnitude, and so forth. So we're working very hard with our colleagues in New South Wales, the NARCLIM team, to produce all of these additional indices over the coming months. As was mentioned before, the Climate Science Initiative is co-funding 2 PhD students at Murdoch. The first student started around December 2023, Tishan Tambipile. When he started, the simulations were not quite ready yet for him to analyze, so we got him to look at the big picture first. So what Tishan is looking at is this thing called the Indian Ocean Dipole, which you may have heard of. As it turns out, the Indian Ocean Dipole is a very important mode of climate variability that affects the whole of Australia. So we thought it would be good for Tishan to dig into Indian Ocean Dipole dynamics more closely. So he recently got a paper accepted in the journal Climate Dynamics. It literally was accepted last week. And that what we did for Tishan's work is we said, let's look at all of these global models, the whole lot. We'll focus on the ones that have been selected for dynamical downscaling, and let's have a closer look at how these models simulate the Indian Ocean Dipole, because it kind of matters for the whole country. So this is a graph from his paper. There's a lot of information in it, but what I'm going to point out here are these red and blue circles. So model 57 highlighted in red, as it turns out, is the no ESM 2mm model. That's one of the models we are downscaling, and everyone else is downscaling as well. Model number 2, highlighted in blue, is the Access ESM 1.5 model. It's also one of the models that everyone in Australia is downscaling. Why does this matter? It matters, for example, if you look at what's happening over here, the no ESM model, right, has very, the ENSO variability, so ENSO is the El Nino Southern Oscillation Index. It's the variability of the ENSO process in that model is a bit off the chart, even though it was selected as skillful. So this sort of information is very, very useful, not just for us, but for all of the climate modeling groups, because everything that's highlighted in bold at the bottom is a model that some group in Australia has decided to downscale. Now, the error that comes from the global model goes into the regional model. So this is very useful context when we're going to try to figure out why we're getting particular errors in simulation of precipitation in the regional models, right? So the second student started May 2025, that's Bikash. He's going to use our 4-kilometer data. Now, Bikash, when he came to Murdoch, came from a very strong renewable energy background from his master's thesis. So he's going to look at how climate change will affect renewable energy resources, wind and solar, in the Southwest. This matters a lot because as we transition to a renewable energy economy, there will be instances where we might have a whole heap of solar but no wind. We might have instances where there's very little solar and very little wind. It matters when you have extreme events such as hailstorms that destroy power transmission lines. It kind of doesn't matter where your electricity comes from. If you can't transmit it, no one can use it. So we want to look at all of these ideas together. And to do that, Bikash has started looking at wind speed simulations from observations and from the model. That's the ERA5-driven simulations. So the plots here are wind speed at Rottnest Island and Badingara. And without getting into too much detail, our model simulations show some improvement. So that PSS score there, the higher the number, the better. You will see that our models do a pretty good job of simulating the distribution of wind speed at these two sites. So this is work in progress. Now, as has been mentioned already, we are a country of drought, well, at least the Southwest, a region where drought matters. One of the things we're very interested in is when we run the model with ERA5 reanalysis, right, when we downscale ERA5 reanalysis from 30 kilometers to 4 kilometers, does it actually improve the simulation of drought? And the good news is, yes, it does, without getting into too much detail on this graph, right? We're looking at the 15th percentile of precipitation, drought intensity, drought frequency, and drought duration. The AGCD column is the real-world observations. That's raw ERA5, and that's the two WRF configurations, the two regional climate model configurations. What is important here is what I've highlighted in red. That plot here on the very right-hand side where it's blue, it means that the model does a better job than the data we use as input to downscale it. So, right, this was very good to see. So the model simulates drought better than the reanalysis that was used as input to the model. Now, Mark and a few, the Deputy Vice-Chancellor, Peter Eastwood mentioned the Great Perth hailstorm of March 2010, right? Costliest natural disaster to have affected the state. So we were very interested to look at how well the model simulates hail. So an honors student this year who just submitted literally on Monday, right, her honors thesis, looked at that for us. So we looked at hail from the Bureau's radar data. So that's the hail events that the Bureau has been able to detect from its radar. I need to note here that these radars, they tend to fail when hail happens because it gets damaged. That happened during the Perth hailstorm, right? So whilst the radar data is excellent, it also misses events because they are not always working at the right time. The plots on the right-hand side are derived hail frequencies from the models, right, the R3 and the R5. Without getting into too much technical detail, one thing that is very well known in our region is that the Goldfields region, so Esperance and Kalgoorlie, are hotspots for hail. They are hotspots for hail because we get a lot of energy coming from the north, and also it gets pretty hot. When it gets hot, you have enough energy to push the air up. So what we can see is that some configurations of our model capture that higher frequency of hail in the Goldfields region pretty well. Now, we are the first study, right, to compare hail frequencies from a high-resolution model against the Bureau's radar. That no one has done this yet, right? So it's pretty hot off the press, and we're going to work hard towards writing this up as a paper next year. So there's other relevant projects happening at the same time. So there's a project called the Western Australian Small Water Cycle and Farming System Adaptation for a Carbon Neutral Future. This is funded from DWER. And that project has 3 aims. The first one is to do a critical literature review of drivers of winter rainfall, cool season rainfall in the Southwest. Good news, we got the paper done and accepted. The next 2 aims is to revisit the impacts of land use change on climate in the Southwest and look at what might happen in the future if we reforest different parts of the Southwest. So the contacts for this project are myself at Murdoch and Kim Brooksbank from DWER. Ian Foster is also involved. Dr. Karuru Mamahiu is the postdoc we've employed at Murdoch, who's leading the modeling work on that. The paper just got accepted on the 29th of October. This was led by my colleague, Kering Hawke, as the lead author, and myself and Ian. We basically looked at all the papers that had anything to say about rainfall decline in the Southwest, and we've synthesized all of these papers into this review. As part of this review, we also came up with some nice schematics that summarize what typically happens during dry versus wet winters in the southwest of Western Australia. We've also generated a schematic of how land use change has influenced convective cloud formation in the southwest. This is all the work that Tom Lyons did during his time at Murdoch. This was also what I did my PhD in back in the day. So that paper is something we're really proud of. It's something that I think everyone has been crying out for quite a long time, because there's a lot of science that has been done to address causes of rainfall decline in the Southwest. There's also a project within DWER, within their hydrology team. So the hydroclimate team at DWER is tasked with providing climate advice for WA water management projects. So they are currently updating the advice. They are going to use bias-corrected outputs, right? So for hydrological applications, you have to bias-correct your data first from CMIP 5, CMIP 6, and also, of course, this project. That work is being carried out right now. And if you want information about this, this is the email to contact. What other data sets are around? We are not the only institution in Australia doing projections. So the CSIRO, the Bureau of Meteorology, New South Wales, and the Queensland government are producing reanalysis, so ERA5 driven and CMIP 6 dynamically downscale projections for the whole country at around about 20 kilometers. That link there will summarize all of these data sets and how you can do that. There is also a Codex CMIP-based, regridded and calibrated data set for Australia at 5 kilometer resolution. The important thing to understand from this data set is that they've taken the 20 kilometer data and they've statistically downscaled it to 5 kilometers. It's not dynamical downscaling, it's statistical downscaling. So even though that data is at 5 kilometers, it's not convection permitting. So whilst it is at 5 kilometers, it does not incorporate processes in the real world, in the real atmosphere that occur at 5 kilometer resolution. But it is a very useful data set. It has been bias corrected, and you can use it. This is generated by the Australian Climate Service, so they are the people to contact about this data set. Now, how are we unique compared to all of the other data sets? The Climate Science Initiative, we are the only project to have dynamically downscaled CMIP6 models down to 4 kilometers for the southwest and soon the northwest over the full period, including the free SSPs. All the other data sets are at coarser resolutions, non-convection permitting. There is that 5 kilometer data set that I mentioned before, that it is 5 kilometers, but it is a statistically downscaled product, right? And of course, our work would not be possible without NARCLIM. So the NARCLIM team in New South Wales, similarly, are the only project in Australia that have produced 4 kilometer projections for Southeast Australia. So together, New South Wales and DWER, we've produced this very unique data set that covers the west and the east. There's some relevant publications I want to point your attention to. So this paper, led by Divya et al. 2022, summarizes in a great deal of detail how we picked the 5 global models that we picked to downscale. Everything you need to know about these 5 models is in this paper. So it's a good one to have a read of. This other paper, and both myself and Julia Andrys were involved in that paper as authors, that paper describes in detail, right, the NARCLIM2 data set that is at a 20 kilometer resolution and covers the whole country. Right, this evaluates the whole, all the 20 kilometer simulations. Now, since these are the simulations we use as input for our 4 kilometer simulations, it's very important to read this paper, right? So have a look at it. This paper also included myself and Julia Andrys from Murdoch. This paper describes in a whole lot of detail the 20 kilometer simulations we did over the whole country, right? And it's important to read this paper because that's the data that we further downscale to 4 kilometers. There's that paper by G et al. Again, that's a paper that myself and Julia were also involved in that also focuses on the ERA 5-driven simulations, but looks at precipitation extremes. So have a look at that. Now, this paper is also very important. As I mentioned, many modeling groups in Australia have done projections that cover the whole continent at 20 kilometer resolution, right? So the New South Wales government has used the WRF model, right? The Bureau of Meteorology uses a model called BARPA. CSIRO uses a model called CCAM. What we did in this paper that included me and Giovanni as well is that we compared all of these models together, right? So how is the CCAM model different to the WRF model, different to the BARPA model? It's all described in that paper. That paper benchmarks all of these different regional climate models that have been used and that cover the whole country, right? So the take home from this work is that there is no one model that beats everyone. They all have strengths and weaknesses. That paper, this is another paper that's recently come out, again, that includes myself and Giovanni from New South Wales. What we did in this paper, again, we looked at all of the projections that cover the whole country, and we looked at uncertainties in the regional projections compared to what the global models tell us, right? It's got very, very useful context, so that's definitely a paper to look at. We will stop for questions soon. We're running a bit over time, but the next talks will talk about data access, so please hold off questions about that, and this is the end of my talk. And No questions, all right, we've run over time. But there will be, thank you.
No. It's very obvious that Jatin has a huge passion for this and he's gone into his question time, but he'll be available here now for questions, and there's also going to be a panel. There's a panel. So we've got a break now for 15 minutes, 10 minutes, to try to keep us on time a little bit, and so that we don't eat in too much to the socialising at the end. So yeah, we've got a break now and we'll come back at 3:25. Data scientist in a range of areas, including machine learning applied to remote sensing, land use classifications for ABARES, which is the Bureau of Agricultural and Research Economics, and mineral exploration processing at BHP. Earlier research was in the areas of remote sensing, oceanography, spatial science and climate science. And Sean Lamb is a Principal Environmental Officer at DWER's Climate Change Initiative. He was mentioned before by Kim. He is a Chartered Environmental Engineer and Climate Scientist, specialising in climate change, modelling and air quality, and he specialises in translating complex science into practical information for policy and assessment application and leading cross-functional teams. Welcome to you both. I'm assuming you're tagging in your talk, and look forward to hearing.
Okay, I'm giving a summary on the product which just got released a couple of days ago, the SLIP product. My talk is on the first 3 points. Basically, I'll cover what the product is, the sources of the data, and the steps that we use to produce it and what is available. And then Sean will discuss the ongoing work for the production of the 4-kilometre data set. The overview of the 20-kilometre data set, as mentioned, it's available at SLIP. That's the website that you can see. The data is saved in CSV file and 3 image formats. That's the shapefile, NetCDF and geodatabase. The products are a maximum, minimum, mean and standard deviation statistical temporal analysis of the model products. That is the 20-kilometre climatic model products. Also, there's a calculation of products which are the difference between the future and present statistics. And all of these have been projected to the Australian standard GDA 2020. An overview of the 20-kilometre data set. Now, the products were produced from 3 climate model products. That is the bias-corrected minimum, maximum temperature and precipitation, rainfall. The models, as discussed by Jatin, were the 5, 6 GCMs that have been dynamically downscaled with 2 regional climate model configurations. And so that's the ensemble. And then there's 2 scenarios, or 3 scenarios. Historical, or base as it's frequently referred to, SSP 126 and the SSP 370. The time periods for the products produced were baseline, that's 1990 to 2009. And that's consistent with the NARCLIM New South Wales product. And then the time periods 2030, 2050, 2070, 2090, and that is an average of 20-year periods centred on those years. and there are annual products and seasonal products for those temporal periods. So, just to show where we started with, or the data set we started with, was essentially the one you see in the top right hand of the image. That's produced by the New South Wales team, and that's been produced from the GCM model as discussed in earlier talks. It's 20 kilometre resolution. It's been reprojected. It doesn't have any CRS set for, and what that is a geographical CRS setting. And that's deliberate so that it can be readjusted essentially for the part of Australia that you're interested in. So our initial step is we started with that data, and the first step applied standard quality control tests, geographical correction applied to correctly locate it over exactly over Western Australia, and then clipping and filtering to remove ocean and land. And by land, I mean the rest of the Australian continent. And as I've mentioned, projection to the GDA 2020 standard. Now, the data processing went through these basic steps. And to give an example, you take the variable of interest, in this case temperature minimum, the models of interest, all 5 were included. The downscaling configuration, both R3 and R5 were included. The period of interest, whether it be years and seasonal, for example, the present, and annual. So that is as an example, in the present period, 1990 to 2009, all months. And I should mention, the initial data that we started with is monthly climate model projections. It's not daily. So that was also the starting point. And finally, the emission scenario to suit period of interest. So for the future periods, 2030, 2050, 2070 forward, there are 2 products. There's that for the high emission scenario and for the low emission scenario. So for those, the mean was calculated, the standard deviation, the minimum and the maximum. And the results were saved, as I mentioned, in the NetCDF, shapefile GDB, and the naming conventions that were used for NetCDF and GDB, it's quite clear how it's named. So there you see the minimum of the temperature maximum, bias adjusted, annual, R3, R5 ensemble. For the shapefiles, because of the limitations of the shapefile format, had to come up with a naming convention which essentially matches that, which means the same thing, I should say. For the geodatabase, it's the same in the case for most of the images. All the information is saved in one CSV file. And if you look to the bottom right-hand corner, you can see the tag unique ID, which is the geographical location of the information. And you see the column D, that contains all the information for one particular image. And as you can see there, there's the names corresponding to the image. So if you were interested in both the image as well as the information in the NetCDF, you just match them. To further expand, an example of the CSV file shows multiple columns of information from multiple images of analysis. And for example, the first has the minimum temperature, bias adjusted temperature maximum annual for the baseline period. The next one is the maximum, and so forth. If you open up in a viewer, a GIS viewer, QGIS, you will see the full name of the data layer, and I should note, in this case here, I've imported 4 of the NetCDF files, 4 of the NetCDF images, using QGIS. If you're using ArcGIS, which is commonly used in the GIS world, I've noticed sometimes that there are importation errors that can occur, so it's just something to be a bit cautious of. The other formats I mentioned, the shapefiles, the geodatabase, that's not a problem. So on the SLIP portal, what you'll see is a description of the products on the first page. So to the left, you see the minimum temperature bias correction. It shows the baseline dates and the future dates. The example on the right shows the 20-kilometre rainfall bias corrected. Then if you go to the next page, you see where you can download the actual products themselves. So, for example, the top one has all of the results for the minimum temperature models. So that's all of the statistics that I've just mentioned will all be in that one file. Additional resources, there's a short introduction to visualising the data using either QGIS or ArcGIS Pro. And then there's the TSI technical information fact sheets and the metadata text files, which have all a much more detailed information of expanding on what I've just basically been saying. Finally, if you're interested in really digging in and seeing which files were actually analysed to produce the final products, you can open up the NetCDF file and go and look in properties, and it will show you all of the actual images that were analysed to produce the products which you're seeing. Okay, thank you.
Thanks, Mark. So for the next 5 slides, it's targeting for technical users. For the southwest of WA CSI project, we've produced 4 petabyte data. So they are graded in NetCDF format. We produce in hourly, 3-hourly, daily, and monthly data. So we produce 150 codex variables, and they are categorized in 5 GCM, and they all have different calendar dates. And under 4 scenarios: historical, SSP 126, 245, and 370, and under 2 RCMs. So the time period spanned from 1951 to 2100. So because the sheer amount of data, the most frequently requested data will be available on the National Computational Infrastructure, NCI. So this NCI is based in ANU in Canberra. The CIMIC data set is distributed by the Earth System Grid Federations, and NCI manages the EFGF Tier 1 data repository. So the CSI is leveraging the state-of-the-art existing NCI data portal to host the most frequently requested data. The benefit of it is like we are integrating the CSI data with other jurisdictional data and all Australia CIMIC 6 data sets. And this will benefit the stakeholders and the research scientists who wants to carry out research and assessments. So, so the data will be available for both NCI and non-NCI users. So the variables that will be available on NCI are the codex core variables, and they are the most frequently requested data as mentioned earlier. So that include surface temperature, maximum temperature, minimum temperature, precipitation, and etc. And the codex core Tier 1 and Tier 2 variables will be on Pawsey. As Jatin mentioned earlier, all the CMIC6 data for Australia are on NCI, and all of them cover WA in coarser resolutions. And you can follow this link to see all data sets. And you can see the CSI data set is already on the data access page. So when it is activated, you can follow this link and use the NCI threat data portal to have access and download the data. And this is like an example of how the data is structured. Like I'm using the New South Wales government, the NACLIM 2.0 as an example because we follow the same structures. So it will be under project code, CSI, and then where the model domain is, and then basically the GZM, scenario, experiment, RCM, and the frequency, and then the variables, and then the time, and then the variables name as well. So, as Jatin mentioned earlier, it's better to get a feel of how to use the data. So this is the Great Perth hailstorm. I used the Year 5 data to simulate. This is the first test of how we can visualize the data because this 4 kilometer CSI data is dynamical downscale data. It's preserved the physical consistency, and it's in a convection permitting scale. So it captured really well with the Perth hail events. So that's the end of my presentations. Yep.
Thank you very much, Sean. Okay, so next we have Julia Oliver. So Julia is the Climate Science Communication Officer for the program. She has a Bachelor of Science Psychology from University of Western Australia and did her honours thesis on looking how likely the Paris Climate Agreement would be at succeeding using a collective decision-making game. So welcome to Julia.
Thanks, Trina, and thanks for reminding me about my honours thesis, actually. It's very interesting. It was not very good, the likelihood of the world cooperating to reduce emissions, so hence we're trying to do all this work to prepare for climate adaptation. So my role in the program, and what I want to take us back to this afternoon, is looking at why understanding our projections is so important. As Kim and others have stepped us through today, the climate is continuing to change. And what we're looking forward over the next few years has also been highlighted in the recent National Climate Risk Assessment released by the Australian Climate Service. We're aware of this work, but we're doing our work and we kind of see our work as supplementary because we're making sure that our results are more regionalised than work happening at the national scale. This is important because we want users in Western Australia to use information from the Climate Science Initiative, and this means that it has to be understandable, not just for our technical users, but also for other people who have to work and consider climate changes in their work. So my focus on the program is to look at the communications products. And what this will consist of is things that are more targeted at less technical users. The first of these will be an interactive climate change projections viewer. And this is essentially a map that you'll be able to go on and look at your local area and see those temperature and rainfall changes that we've been showing you, but in your local area, and you'll be able to click on a grid cell and look at that change in different areas across Western Australia. Another way is through producing fact sheets, summaries, infographics, and webinar sessions like today. We also have a regular newsletter that goes out to our stakeholders, and a lot of you would have found out about our event through this method. To inform some of the communications work that I've been doing, we ran a study that Brianne Robinson-Ellis from the DWER graduate program helped us with to help us understand who our users were. And we came up with a framework broadly consisting of 4 different user types. This started with people who were kind of more beginner users of climate information and might be generally interested in climate change or just coming across the information and seeing what it's all about. Then we have people who are a bit more capable, like government risk officers or local government people who might have to start considering climate change, how it affects their businesses, and they're looking for high-level information to help them make better decisions. We then have our more intermediate users, like specialist risk assessment or insurance people who use climate projections of the future to inform their work. And finally, we have people like Jatin, who are researchers who are very familiar with the climate science, and we also have a bunch of technical consultants who are interested in our work and scientists that are doing comparison work across Australia. The reason that this is important is because of the arrow that we have here. We want people that are beginners to use our data and be educated in sessions like today so that they can move along back and forth and get better at using climate science in an informed way. We found in our user assessment that there are a number of barriers people use when they're trying to access climate material. And some of these are that the variables people are looking for aren't there. Some people don't just need temperature and rainfall, they need that full cortex list that Sean's spoken about. They want to know about surface humidity, or they want an index that they can use. So we're really trying to make sure we make as many variables available as possible. There's also a lack of training and guidance and people just not knowing how to get their foot in the door and their hands on the information. So we've used this information to try and come up with ways to overcome barriers, including firstly by creating a single point of information. So we've really tried to make sure that everything we've spoken about today is available on our CSI website, so you can go there and kind of step your way through. And we've also got our regular newsletter to help. To engage our users, we send regular email updates, so if you're not on our mailing list, I'll show a link on how to get up there later. And we want to make sure that we work together with users such as yourselves as we enter this next phase of data. So we've just released this 20-kilometre data product yesterday, and if you have feedback on it, please talk to the team. We're really interested to hear what you see and ensure that how you use this product shapes what we produce in the next phase. So this year we've produced a number of communications products. On the screen here you can see some of our infographics. So you've heard Access ESM and ECVEG thrown out a lot today, but this is just, another way to point it out. If you're someone in a risk officer role and you're trying to brief a busy executive and they're going, why are you giving me results for 5 different climate models? You've kind of got this illustration to show with pictures. One of them's going to show you a future that's hot and dry, and one of them's going to show you a future that might be higher. There might be events that, are wetter, but they're more rare, and we need to consider all of this information. So there's about 5 of these on the website now, and we're very happy for folks to take screenshots of these, use them in briefings. That's what they're there for. We've also released a big set of FAQs on the website about our new data and about the 20K, the 4K, the differences. So go there and have a look, and as well, please feel free to use that information how you see fit. One of the fact sheets I would read if you are going home and all of these terms were new to you is this one. So this is called Everything You Need to Know About the Latest in Climate Modelling, and it has definitions of RCPs, SSPs. It talks you through the transition between these different generations of climate modelling, and it has, just a really good understanding of what we're doing, and is the first fact sheet I'd read in our series. Another one which Jatin mentioned that's really important is the convection permitting modelling fact sheet. Now, we spent a lot of time developing this, so we actually worked with the New South Wales government, the Queensland government, and Scientel, who are experts in climate science communication. So this one's written in quite plain English, but it's also backed by a really extensive reference list of peer-reviewed papers. And it kind of gives that evidence of why using convection permitting modelling is important. And if you're trying to justify, why you might be referring to the CSI data, you can link this fact sheet and also see those papers there as well for why that type of modelling is important. I do want to acknowledge, because from a stakeholder needs perspective, there are a lot of climate data sets out there. So there's various tools, and you've probably heard the Australian Climate Service has recently released a portal along with their NCRA and also a CMIP6 data set. And to try and help people to understand all these data sets, I actually work with the National Environmental Science Program's Climate Systems Hub, and we have 2 guides that have come out that try and summarise all of the portal information happening across Australia. And also the second guide there can help step you through how you might want to try and select the information for your needs. So here I just have a little screenshot of the first fact sheet. And for example, you can see on the left, there's multiple pages. It's not just national, it also steps you through each state and territory. But you can see that, you know, different scenarios are using different baselines period, like we kind of talked you through. The reason the numbers are different might be because some people are using the 1986 to 2005 baseline and some people are using different ones. So this kind of lets you just at a high level jump in and see what different folks are using and kind of answer that question of why you might be seeing differences. While I'm mentioning it, I will just quickly plug the Climate Systems Hub because I work as a knowledge broker with this group. They're doing research across Australia, and I work with a team of interjurisdictional partners to try and make sure that WA interests are represented. So if you do ever come across Climate Systems Hub research and you want to be involved, you might have heard them through me before, please just shoot me an email and I can put you into touch with researchers at that national level. I've got 2 slides. The last one is on what's to come in the future. So one of the things that we're really focusing on is the Climate Projections Viewer. You can see here we have examples from South Australia, Queensland and New South Wales. And we're going to build one with our side of the state on there, our side of the country for WA. So we're currently working through the procurement process, but as soon as we have a vendor on board, we will be working very hard to get that ready for you in the next 12 months. Where to find more information, please go to our website. Please come up to us in the talks afterwards and join our newsletter. Thanks.
Thank you very much, Juliet. So, yes, we will have time for questions about all of this in a very short period of time. Our final speaker for the afternoon is Omer Mughal, is that the right name? And Omer is a senior climate modeller at DWER. And he's also providing technical direction on the Perth heat modelling project. And he's previously worked at Singapore, where he provided UHI, which I'm assuming is Urban Heat Island. Urban Heat Island estimates and quantified Singaporean mitigation measures that helped identify the Urban Heat Island as a policy metric. And I'm really interested to see what you have to say. Thank you.
Thank you very much, everyone, and good afternoon. I'm going to speak about some of the applications of the CSI modeling data set from slightly different angle. Previously, Jatin has spoken about a lot of other projects, but I will be focusing on like a further higher resolution, which is like a kilometer scale. You can imagine it as a city scale. So all the applications focus towards the Perth region. So the first project is the Perth Heat Modeling Project, as I've already been introduced about. Firstly, what is the urban heat island effect? Cities are warmer than the surrounding rural areas, somewhere like 3 to 10 degrees Celsius. The reason being heat retaining surfaces, reduced vegetation and natural cooling, waste heat emissions from vehicles, buildings and industry, urban geometry that traps heat and restricts airflow. What are the impacts? The heat mortality and public health risks such as the heat stress and impacts on the air quality. There is an energy demand surge, and there are also some local climate shifts. UHI can alter the rainfall patterns and prolong heat waves, which Julia has already touched about in her talk. So what is the heat wave definition? A heat wave is when maximum and minimum temperatures remain unusually high for several days. We are at plus 3 degrees Celsius, using like the global warming level, heat wave duration is expected to rise in the northwest of WA from 4 to 22 days annually. And this is from the Australia's Future Climate and Hazards Report that was recently published. You could see the two graphs that are showing like, on the top graphs, they are showing like the hottest day of the year at this +3 degrees Celsius warming level. And they also like the severity of the heat wave days at the same warming level. You can also see like how the temperature is trending, which has already been mentioned by Paul in his talk. And like there are various temperature extremes that Perth has hit over the past couple of years. The most highest of them, which is the record high, is 49.5 degrees Celsius, recorded by the Bureau of Meteorology, and it's also been reported by 9 News. Within our, urban heat is an increasing concern for Perth's livability and health, as I've mentioned earlier. In 2019, a paper was published where we looked, where the researcher has looked towards UHI awareness versus UHI reduction measures, and cities were given certain ranks. We can see that Perth was ranked lower compared to the other cities, and since then several other initiatives have been tackling this issue. For example, some that have been taken in by WACOS, and there are also urban greening strategy that has been recently introduced. However, there is still limited detail data to understand and predict UHI, particularly at a city scale. And CSI data will be downscaled to that scale to deliver practical insights for managing urban heat. So as a part of the state's climate adaptation strategy, there is a project that that is led by DWER's Air Quality Branch to model Perth's future urban heat island effect and inform local adaptation planning. Our focus is to generate high-resolution data sets to support local planning and resilience strategies. I would like to mention here that this only focuses on the data sets, not on the mitigation measures. Then the CSI is a critical foundation for our work, providing future projections. We are trying to use like the best available urban data sets. These include surface cover and building data from Geoscape, vegetation data from satellite, and downscaled climate projection from CSI. Validation will be supported by observed climate data from AGCD, BOM stations, and also from DWER monitoring station, as is mentioned in the figure at the bottom corner. So this is like a very brief summary of the CSI data integration methodology. We are aiming to first do like a baseline UHI characterization, and this is underway at the moment. Then there is like data alignment step where we match climate and land use data to model grids for accurate simulations. Then there will be another level of enhancement where we add finer scale modeling to better capture urban temperatures, and then assess UHI under low and high emission pathways for future scenarios. We are also doing some environmental modeling. There is already a proposal that is for the stationary monitoring network, specifically focused on UHI, and there are 40 fixed sensors for model validation. Their coverage is from Cervantes north to Collie in the south. It will provide real-time insights to UHI impacts in Perth, and then the sensor placement is guided by an environmental plan. We are also doing some mobile monitoring campaigns, and it complements the stationary network with high-resolution spatial and temporal data. We get flexible targeted measurements under specific conditions, large-scale coverage without dense fixed infrastructure, and it integrates temperature, humidity, and GPS. You can see like the high-res temperature that has been obtained by a mobile monitoring campaign, and you can also see the vehicle on which the measurement instrument is mounted. So this is our project timeline. You could see like we have already reached to the end of 2025. We expect to complete our baseline study by the Q2 of 2026. By that time, we will get like the future UHI bias corrected future projections for southwest of WA. And then we move on to complete our war fronts by the end of 2026. Within quarter 3, we intend to implement our modeling data sets to SLIP and then publish that at the end of quarter 3 of 2027. So this, I come to now the second project that we are looking towards. It's like the sub-hourly extreme precipitation. This is a joint project with various institutes that you see the logos on the screen. Why are we doing high resolution modeling for this one? Because flash floods are driven by short intense rainfall events, and it causes infrastructure damage and overwhelm stormwater systems. It can damage transmission lines, roads, etc. Climate change may increase the intensity and frequency of these events, and accurate estimation of rainfall intensities for short durations require high resolution modeling. And this is what we emphasize in this project. So SHEP, as we say, will deliver finer scale sub-hourly rainfall data, filling CSI gaps and supporting a national urban climate initiative. This project initiated in 2023 by National Environmental Program and National Partnership for Climate Projections, which were, and this erupted from the discussions aiming to address climate-driven changes in sub-hourly extreme precipitation. It got official endorsement in 2024, and it was marked as a flagship project. And then it aims to analyze, model, and project short duration rainfall extremes at high resolutions in Australian cities involving stakeholders across Australasia. Its impacts include advanced understanding and modeling of sub-hourly extreme precipitation to inform climate risk assessment and support end user decision making. So this project basically contains 2 activities. Activity 1 is event-based analysis, where we look at the events from the AWS, which we say automatic weather stations, and then verify if the same events are shown in radar and by a high resolution reanalysis data set by a BOM, and then verify whether the media reports also report these events to be as severe and their impact is visible in those media reports. So this is a part of activity 1, where we have identified potential AWS stations across Perth. We have extracted extreme events at sub-hourly scale and also at hourly intervals, and then validated that 10-minute extremes align with hourly extremes. This is the 10 of the extreme events that have been identified by this analysis, and out of these 10, we have selected 4 by cross-verification of AWX extremes with BOM high-resolution analysis and cross-validation with extreme from Perth Serpentine radar. And it does include that 2010 hailstorm. So this is what I will describe here, that you have already heard about this hailstorm in various talks, that on March 2010, Perth was hit by its priciest natural disaster with record hail, flooding, and wind causing over $1 billion in damage, widespread power outages, and major disruptions across the city. So our progress model areas have been defined. We have defined a consolidated modeling setup adopted across project teams, and then new tools have been developed to link local climate data with the model framework. Our next steps include combining model outputs at a kilometer detail to better represent Perth's climate, add realistic urban features such as the local climate zones or high-resolution urban climate parameters, and then simulate Perth's future climate under a +2 degree warming, and conduct long-term climate simulations for trend analysis. So what are the takeaways for decision makers from my talk? Extreme heat and flash floods may threaten infrastructure and communities. The high resolution modeling, as I said, and as you have listened, that it's essential It enables accurate prediction of urban heat and short duration rainfall extremes. CSI data is critical. Again, I emphasize on that. Enables downscaling from 4 to sub-kilometer, and it's also based on the convection permitting modeling scale, and is based on physical modeling. So our action now is to integrate climate insights into urban planning and adaptation strategies for a resilient future. Thank you very much.
We have a wrap-up.
Thank you, everyone. We thought, just before we go on the panel discussion, that we do a bit of a wrap-up of everything. So myself and Paul are going to do that now. I think you have.
So there's a lot of information that's been presented today, and it's pretty exciting, this capability is being developed in WA. So just highlighting again, this is the first time that WA state government has partnered with a university to deliver high-resolution information for WA needs. It's pretty exciting. The intention here is really to try and prepare Western Australian, everyone actually, to get on with the job of climate adaptation and mitigation. There's quite a number of government agencies that are starting to be empowered to start their sector adaptation plans, and the CSI inputs to that and the knowledge that is being developed is going to be a key resource, I think, really to try and turbocharge progress in that space. So building a sustained climate science capability, meeting WA needs with WA resources is really the core of this project, and it's something that we're hoping that we can continue to build and cultivate over time. And some details from Jatin.
Thank you, Paul. I just thought it's very important for us to highlight what has made the work possible. So the CSI really is a piggyback project on the New South Wales NARCLIM project, right? So without them, we would not have been able to do any of what we've done today. So I just want to highlight that. So the New South Wales team, led by Giovanni Di Virgilio under the direction of Matt Riley, they sent us the 20-kilometer data so we could do the 4-kilometer simulations. We transferred, right, over a petabyte of data from New South Wales to Pawsey. That's more than 1,000 terabytes of data. It took a lot of effort, both from our team and the New South Wales team. Things go wrong when you download that much data, right? It's not an easy thing to do. Other things that the New South Wales team, the NARCLIM team, led by Giovanni, they've provided us all the codes, the software to do the BAS correction, the post-processing, calculating the hazard indices, doing quality control and assurance, right? When you're running that many simulations, things go wrong all the time. So we didn't have to reinvent the wheel. So without their help, it would have taken a lot longer. We've done a lot of knowledge sharing, right, between the New South Wales team and the WA team. And if we had to do this from scratch, if we had to take the global model, first go to 20 kilometers, then go to 4 kilometers, it would have taken more than double the amount of time and more than double the resources, right? This is not only, it not only takes a lot of computational resources, it requires a lot of people, right? This is not a one-person job. The second partnership, I think it's really, really important, is the Pawsey Supercomputing Research Centre, right? That point has been made many times. You can't do this work on a desktop. You need a national facility. If we were to go to a commercial provider, so there are commercial providers of high-performance computing and storage, it would have cost many, 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 many millions of dollars, right, to use a commercial supercomputer and to use commercial data storage. It would just not have been possible at all, right? At that point has already been made, but we've got the largest possible compute allocations at Pawsey for 3 years in a row, and we probably have one of the highest data storage allocations. This is very significant. To complete these simulations, We've submitted millions of jobs on the supercomputer, right? All that workflow had to be developed. And without the help of the Pawsey help desk, right, this is very technical work. Things go wrong all the time. You have to change and adapt without, it's not just a supercomputer, it's the people who make it work, right? It's very, very technical work. So without them, we would not have been able to achieve any of that. So university and state government partnerships with a center like Pawsey are critical. Like, we can't do any of it without these partnerships. So I just wanted to highlight that a bit more. And so just quickly, the 20-kilometer bass corrected data that's created by the NARCLIM team in New South Wales is now available on SLIP. The 4-kilometer data, we haven't bass corrected it yet, will be available at the NCI, as Sean has explained. This is going to be predominantly for technical users. And just to give you a sense of where we're at, we just got the contracts done with the NCI last week, and we just got the email this week saying your project code has been set up. Right? It is happening right now as we speak. We're working as fast as we can. We're also looking into setting up like a mini cloud computer, so that will be via the ARDC Nectar Cloud at Pawsey. This will be a smallish system, but it will still be an avenue that we can provide people with data access and compute. The projection viewer will mostly be for non-technical users that will give you high-level summary data and not, hundreds of terabytes worth of netcdf files. So that's kind of where we're going. And I'll just go back to Paul for the final timeline.
So people have seen this before, but just to highlight again, we've got the first tranche of data, this 20-kilometre projection data that was available a couple of days ago, actually. And we've got a series of other milestones that will be met in the early 26 through to the end of 26 as well. Just to note that all of the information that has been presented today will be made available to everyone. So there's a lot of detail. You'll be able to get access to all this information as well after this session concludes. So thank you very much. A panel discussion to follow shortly. But one thing that we really did want to try and highlight again is just acknowledgements for people that made the event today possible. So just calling out some people explicitly. This has very much been a team effort, but at DWER we're really very grateful for Julia and also for Kim for being right in the trenches here of getting this event organised. At Murdoch, both Catherine and Dannon as well have really helped us out here to try and pull the event together. The CSI team more broadly and the partners, importantly, both Pawsey and New South Wales as well. And very much thank you to Tran and the Harry Butler Institute for hosting us here today and for some great snacks that we're going to have pretty soon as well. So thank you very much to everyone. We've got a panel that starts right now for questions and answers.
So yes, we've got we've got a panel discussion between you and snacks. So if you want to ask long questions that take them half an hour to answer, or if you want snacks. I don't think I need to be involved in this. I'm not going to stand here. I think there will be a couple of people with microphones here, one. And if you have a question like to ask and you want to be the first person, you could already put your hand up. Okay, we've got our first two questions.
Hey guys, can you hear me? Yeah. Awesome work. One of the things I'm really interested in is like dataset availability, right? And like one of the technologies that has like come ahead leaps and bounds in the past few years is like virtual ZAR, which makes it very, very easy to download a lot of data. I saw you guys were setting up the Nectar ARDC instance. Do you think it would be possible to virtualize the datasets and provide public access through that? Is that something that people would be interested in doing?
So you're talking about the ZAR Yeah.
Virtualization, yeah. So just cache the metadata into a reference and then make it available through that as if it were a ZAR store.
It's not something we've thought about or planned for, but if it's a better way to share the data, I think we'll certainly should look into it. I've heard of the ZAR technology, just quite broadly, so I don't know a lot about it, but yeah, it's something we can consider.
One of the things that we're really keen for is for people to get access to these data sets and to use them. And so, the 20K data sets are the beginning. As presentations have talked about, it's a challenge to try and move these data sets around. Moving them to NCI means that we do have, resources in order to make these, data sets available if people have compute at NCI. So I think table that query to see if there is some way of actually trying to make these, data sets more accessible, IO, etc., would be great to think about. At the moment, that's not something that's been thought about within the project. And if you've got skills and resources to help out with that, that would be an excellent thing to try and work as a team work on. This could benefit NARCLIM as well and some other state-based activities. So I think the more that we can learn together, work as a collaborative team and try and really extract as much information out of these data sets and the investments that we've made would be an excellent thing to do.
Firstly, thank you to CSI team, particularly Jatin and Julia, who have facilitated me or DVCA RES to access the data at Pawsey Computing. My question is very quick, two questions. The 4-kilometer grids data sets, are they going to be in GDA 2020? Because at current setting, is still in rotated coordinate system, which is, I believe, it will give a little bit nightmare to other people who don't have access Python to convert that into a normal GCS. So that's the first. The second one is the hourly data sets, will it be also posted at NCI? I think Sean's presentation only 3 hourly and daily. But some modeling, like for my modeling, needs hourly data set. And I believe other people, modeler, also require fine resolution of data sets.
Yeah.
Thank you.
So the data that we're going to put on the NCI is going to be in the model's rotated latitude, longitude grid. So the reason, I know it's not the preferred format. The reason we like to leave it that way is because that's the way it comes out of the model. So for those of you who are wondering what we were talking about, so because the Earth is a sphere, when we define the domain where we're going to simulate the climate, it's not a regularly spaced grid because it has to take into consideration the curvature of the Earth. Now, international conventions say that for the part of the world we are in, a rotated latitude-longitude grid is the best way to go to capture the weather systems as they propagate through. Now, that domain itself, as you mentioned, is a bit problematic because it doesn't have a datum, a specific datum attached to it. But what we can do, and I suspect the New South Wales team faces the same common issue, perhaps we can provide tools to help people reproject, and that's been done with the SLIP data, right? So also, one of the reasons we keep the data as it is, like the climate scientists who are going to use the data for climate science purposes, they generally prefer to keep it the way it is. Don't mess with it because we want it as it comes out of the model. But I think there will be tools available to help fix that. Yes? the hourly data sets. So the hourly data, so so some variables we've outputted at hourly frequency. That includes precipitation and temperature. The problem with that is because it's hourly frequency, the files are gigantically huge. And it's very difficult for us to provide all of the data from all of the models all at once. So this is going to be, we're going to have to play this one by ear. So for people who want hourly data for the whole period, for all of the models, we are probably going to have to come up with some arrangement whereby we might put that data on the NCI for a short period of time. People do what they need to do with it, and then we take it off. Or we might have to try to find a way to provide better direct access. So something else with 1 hour data is you don't want to download it. Don't do that. It's too huge. So you want to access it and run your code on the same platform. Right? So that is kind of tricky. So we'll see how much we can manage to put at the NCI, but it will have to be on a case-by-case basis, yeah, for the hourly frequency. Even 3 hourly starts to get quite complicated pretty quickly. Yeah.
My name's Liz. Thanks so much for all your information. I think my questions are more around the sort of application and guidance of some of this information. So one question being, at the moment we're sort of tracking at the high level of emissions. So my understanding is that the scenarios are going to diverge at a sort of, there's a sort of lag before they're going to diverge just because of the emissions in the air. And, you know, they're all sort of tracking it a similar way, and then they might diverge depending on the amount of emissions reductions that occurs, and that's sort of to be determined. So that's one question, is that's not really clear. I guess at the moment, the way that we're talking about it's just very academic, and here are the models, here are the scenarios, but it'd be nice to have some interpretation of what our understanding is of where they're going to go. So just some comment on how that might come in with your communications, and also, sorry, my second question is coming, just give me a minute. It was around where, I guess you've done that historical information and the observations, and I come from a local government where we looked at the data in 2013, then we've looked at it more recently, and the way that it tracked sort of currently based upon our understandings 13 years ago, we were seeing greater impacts than what was predicted in the short term. So I guess I'm just curious to see, are we seeing a higher impact, higher drying, less rainfall, when you're comparing those sort of projections? Yeah, I don't know if that actually is clear what my question is, but I guess we were starting to see, or imagining what we were seeing was more severe impacts than what was originally thought.
I can have a go at trying to answer. I think what your questions are, the first one was scenarios. Are we going to be responsive to updates to scenarios? So the answer is absolutely yes. I can put an IPCC hat on and say one of the discussions that we've had in the early discussions, actually, Jatin and I have been involved in, is trying to get a handle on scenarios. So you may have seen RCPs. You may remember, if you've been around long enough, SRES, if you've been around even longer, IS 92, and then also the SSPs more recently. All of these different scenarios are snapshots in time of where we were tracking. The good news story is, as was in the slides, is that the RCP 8.5 and the SSP 585, the 8.5 is the key part there, across the two different generations of CMIP 5, the RCP 8.5 and the SSP 585, they are now not considered a plausible scenario. We've actually kind of pulled the curve down somewhat. In the discussions around the scenarios for the CMIP 7 project, which is being planned and is not currently delivered data yet, there are new scenarios again that are considering all the changes that are happening. The good news story is that it looks like the scenarios are pulling down. There is, it's not as bad as we thought it was decades ago maybe, but then the sensitivity of the models and the sensitivity of the observed climate, which is the point in your second question, that's something that we still need to continue to try and understand better. The models are imperfect. Jatin said this, absolutely right, but they're also our best quantified information. We're lucky that the laws of physics are actually bounding a lot of the model responses, whereas things like economics are a lot less constrained. So these are the best tools that we have at the moment to try and answer these questions, and an intention of this project and this capability is to try and be as responsive as we can be as new simulations are available, as new scenarios are available, and also trying to keep track of what is actually happening in the observed system, because there is a pretty considerable lag between what the model scenarios at the moment are being discussed today, but simulations that are using those scenarios will not be available for a couple of years likely, and we're always going to be playing catch up. Having said that, the information we're getting from these models, we can interpret them, and with climate science knowledge, you can actually get a lot of information out of those to try and calibrate to what is happening real time. So I'm hoping that answers your questions maybe.
Larissa Taylor, first of all, to everyone sitting up here and everyone else involved, just a massive thank you. It's clear the amount of work that went into bringing this to fruition, but also how valuable it is to the state. And now it's incumbent on all of us to upskill ourselves on how to best use it to make better informed decisions. So I work at the interface of sustainable finance and agri and fishing supply chains. I'd like to know, probably a question for you, Paul, or maybe Julia. Are you going to be producing comms material that we can use at a local government grid level, at an IBRA biome grid level? Because we're going to have to be doing forward-facing scenario for climate, water, biodiversity. I'm wondering about how we can overlay these data sets. And also at the ag zone level that my colleagues in the ag department use, and that's particularly important for the capacity uplift we need for anyone making capital decisions around our food.
Hello. Yes, so in terms of, I guess, the first part of your question, and more broadly for people who are looking for the kind of materials that are more accessible to a local government audience, or more broadly to be able to be shared around, that's where the climate projections viewer comes in. But it's also, we have discussed, and it's one of the products we're kind of considering at the moment, producing regional summaries, which other states and territories do have, and they kind of break the state up into 8 or 10 different areas and produce summary statistics at a high level for temperature, rainfall, and those are like more of a glossy kind of brochure that you can take out to community workshops and share the information in that way, because not everyone is going to be able to go on and play with the data that Mark's produced or the 4-kilometre data that's coming out. In terms of for ag-specific regions, I'm not sure. I guess if you are able to engage someone who can break up the data that is available at 20-kilometre into the regions that you're looking for, that could be something that's really useful. You might need to get a consultant to help, or you might have the skills, but we're also willing, like we can have a follow-up chat with the team on how we can help you to do something like that, because I'm sure it would be possible. And local government, I think, LGA areas, yeah. And that's one of the things. So when we are developing the viewer, we'll need to consider and prioritise the different ways that we'll be able to break up the state. So one of those already in my list is 100% local government areas, so that the summary statistics will be available for each of those, as well as the regional development commission zones, and really interested to hear on what the most useful ways to break that data up are.
Yeah, one of the other things I'd add too is that there are quite a number of sector adaptation plans that are focused on sectors that may be, in small regions or not. And so I really do think we really need to start a dialogue about the needs. We've got these great data sets that we're going to continue to produce, but how do we make sure that they're usable and useful, and how do we make sure that the information that we're generating is something that actually hits a really broad target. There needs to be a dialogue with that too. And as I said, the 20-kilometre data is out now, so hopefully that's starting to kind of hit people's needs. But if it's not, we just need to start that dialogue pretty early and make sure that we are actually connecting the needs, the answers with the data that's generated. I'd already note that across the DWER team, there's a lot of adaptation risk work that's going on, and there's a huge amount of dialogue that's happening. So the hope would be that these data sets are made available and feed into that pipeline, and we can really try and help one another out. But we need to keep communicating really well.
Hi, I'm James Doogie, part of the broader adaptation team at DWER, as many of you know. So a ring-in question, and a question without notice, actually. Interested to hear from Jatin or Julia, Andrys, in particular, in terms of climate attribution science and whether, the work of the last couple of years through the Climate Science Initiative has evolved your thinking around the level of confidence we can put on attribution of human-induced climate change to some of the key observed trends that we've seen, like reduction in rainfall. I'm thinking about, in terms of the findings from your review paper on the impacts in the Southwest as well.
Yeah, so attribution science is around finding the most likely cause for an observed trend, for example, the decline in rainfall. So when we did the review paper on all the causes of rainfall decline in Southwest Western Australia, we looked at a whole range of studies, include paleoclimate studies that go way back in time, well before the observational period. So papers that have looked at past droughts across Australia, including the Southwest and the Southeast, have shown that based on the paleoclimate data, there is evidence that similar droughts may have happened in the past. But all of these studies also show that the current drought we are experiencing, and when it happened and its intensification, certainly has a human influence attached to it, and that there's very, very high confidence in that. In terms of IPCC work, if you look at the change in precipitation across the whole country, the whole of Australia, from all of the CMIP6 models, and you look at significance, so where the change is not just statistically significant, but where the models agree on the sign of the change, the Southwest is basically the only region in Australia where the models agree. So all of this taken together gives us high confidence. In terms of can we use the CSI data for attribution, we can't use it directly unless we run simulations which do not have the human anthropogenic forcing in the simulation itself. But I believe others are working on that. Yep. You have anything to add?
Well, thank you, and thank you all, everybody, for being here for this event. We've got wonderful refreshments out there, and I think there's a bar, cash bar maybe, I'm not 100% sure. I haven't been filled in on that. There are people on the stage that haven't had an opportunity to say something. I thought I would ask you a question, and you can pass the mic along from one to the other. I think maybe it's something like working on this project and working on this project together. Is there something that you would like to say about the Climate Science Initiative as a project, and where you think it sits in the world, perhaps, and what it means to you personally, even? Start with Julie. Yeah.
I chose a good seat to sit. No, so for me personally, just in terms of a reflection for this particular downscaling project we've been doing with CMIP6, I think it was about 12 years ago we did CMIP3, and yeah, we worked very hard, we did a lot of simulations, we had some really, really great data, and we had some interesting papers that came from that. But the problem we had at that point was we didn't have the means to sort of share and distribute that data. So, you know, there was a few papers sort of that resulted from that work, you know, in terms of people taking that data and running with it and looking at, I think there was some winery work and some hydrology work as well. But it's really wonderful to sort of be in this project now and to sort of be in a room like this and be talking to so many people and having the support from, you know, DWER to see that this data now that we've produced and the work we've put into it is now going to be used, you know, hopefully really widely, and hopefully you can all take advantage of that. So for me, just to see that progression in 12 years it makes me really happy. So.
Yeah, no, for me, this is really the culmination of like decades of work. So I remember when I was finishing my PhD, which had nothing to do with regional climate modeling, I thought, we should really do this. So I started half a paper on the side while finishing my thesis, and then Julia was just starting her PhD with the same supervisor. I said, Julia, hey, here's half the work, you finish it, right? And then I went off to UNSW, and then Julia took that on, completed what I had started, and then the rest was her PhD, which was CMIP-free downscaling, right? And then when I came back to Western Australia around 2015, one of the first things I did was drove to DWER, had a chat with James, and I sat in a team meeting at DWER, and I said, we need to do this, right? And it took a while, but eventually the funding came through and all that, and then here we are. So I think, yeah, I feel very proud of where we've reached, and my hope is that this now becomes more permanent, like we keep doing this sort of work.
Yeah, thank you. From my understanding, like, it's been a pleasure working for this project. Being a part of CSI is a big thing, and then like the other thing is that for me, the most interesting thing that I can understand now is that getting your interest involved. So I can see like you've been really interested in getting that data, and the most, you know, like, how would you say, the most important aspect is that like we've got the stakeholders involved and we've gained their interest. So that's the major thing that is, and it's a major outcome of this project. I'm really happy about that.
Yes. For me, my background, since I work with energy and water, and I came back to Australia 3 years ago, and then I was involved with DWER on climate risk, so that's how I was involved with climate change. And then, but my background, and then I moved to DWER, working as program manager for this program. And with my background as a program manager, it's very interesting because even, you know, I'm not a real climate scientist, but working with multiple stakeholders, people from different backgrounds, and try to understand the needs and the gaps and how can, you know, produce things according to the needs and gaps, and yeah, and working with multiple stakeholders. So this is very interesting.
I guess from more of a personal standpoint, it's just nice to know, you know, graduating university, I'm very, very new to this space. I have a psychology background and my thesis was a very depressing year. So it's really good to see that something's actually being done and that people actually care. And I guess as a young person, I'm still under 30, I still can tick that on forms. There's a lot of anxiety about the future. So it's just really good to work in a team where my work feels like I'm doing something to help with that.
Personal perspective, I think if I was to choose a single word to describe this, I think exciting is the word that I'd choose. And the reason I say that is that I left Western Australia in 2003. And at that point in time, IOSI was kind of activated, but it wasn't really something that had, well, I mean, it did a lot, but it didn't gain the same attention. I think that CSI has the potential to actually kind of really engage a lot of agencies and get data out and really get that dialogue going and getting onto the job of dealing with climate change, because we are dealing with it right now. I think one of the things that has really excited me, I think, is I've been here for a month, basically, a month and a little bit more than that. But across all the agencies, across everyone in WA, you've got 2 climate change ministers. You know, the state is really trying to proactively deal with the challenge that we've got in front of us. And I think CSI really does set up the state with the best information that we've got at the moment, with an intention, as Jatin and Julia said, of really trying to turbocharge this and get this moving to make sure that we can connect the best information and data with the needs as well. So I think it's a real opportunity. I'm glad everyone that's turned up today is hopefully sharing that vision and opportunity here, and very much trying to deal with climate change, because it is something that we do have some control over dealing with this. We are going to inherit a lot in the West or in Australia, but we can try and deal with, you know, the best hand that we can through getting on the front foot of adaptation and mitigation planning as well.
Personal perspective, like I think when I first started job, I think John sent me to learn Wolf. Thank you, John. And then Mache offered this cloud for free, like thank you, Pawsey. So it's like everything's kind of in line, and then Jatin say, this job is coming up to do climate modeling. Say, oh, okay, why not? So this is quite rewarding to be able to run this model. I think this is once in a lifetime opportunity to do this CMX6 productions. I'm not sure if that's going to happen again, CMX7. I hope it will be. But what's more rewarding is to see people starting to use the information and helping people to address the climate risks, and they're making good use of these informations for their needs. And I hope it will continue.
I joined the project about a year ago, so I'm relatively recent. And similar to Sean, it kind of came about in an indirect way. Personally, I find this project, or being involved in this project, that I consider to be very important because of what climate change is and the risks and so on. I just see it as being very lucky to be involved in a project where I can apply the skills that I've got to such an important area. And also, on a more, I suppose, selfish point of view, I also have strong interests in computing, as well as just the Earth system sciences. So it's pretty broad. Yeah.
Okay, thank you. That was really great, actually. I really enjoyed all those insights. Can we have a round of applause for everybody, please? And I declare the event finished. I think you probably need to stay there and have a photo, I'm imagining. Yeah. So don't go anywhere.